All right, class, welcome to the urinary system. We're going to be talking about a lot of stuff in this chapter. So a lot of detail, a lot of information. Make sure you take good notes and buckle up, enjoy the ride. Let's get started. So when you think urinary system, you probably think kidneys more than the other organs in the area. You probably don't think too much about the ureters or the urethra. And you're correct. We're going to be talking, 90% of this lecture is going to be on the kidneys. And then we'll save the bladder and everything else, the last 10%, very small details. So kidneys, that's going to be our focus. So when I ask you, and if I was to say, what is the main job of the kidneys? Most of you would probably say it makes pee or makes urine, right? And you'd be correct there. But some would say they filter blood, and that would also be correct. But as we've seen in multiple chapters this semester is although organs do have one primary or main function, they can do 16, 17, 18 other things as well. And it's no different with the kidneys. So the main job, what we're going to be doing, is we're going to be filtering our blood. And if you look down here where I'm putting filter, we're going to be getting rid of all the junk, all the waste inside of our bloodstream, the stuff we don't want floating around in our bloodstream, right? Any toxins, drugs, waste from our food, anything that's just not good long term, we're going to get rid of. Now, by doing that, by getting rid of all that bad stuff, we're also regulating how much water is in our body. Because what do you think the main ingredient of your urine is? Yeah, it's liquid. It's water, right? Unless you're extremely dehydrated. But even then, I mean, it's still liquid. It's water coming out, just not that much water. So if you are really dehydrated and your urine is a very dark yellow, maybe orange brownish color, that just means you have a lot of solutes floating around. And a solute is just anything floating inside of the water. So it can be anything. It can just be sodium, it can be potassium, it can be all sorts of different ions. It can be creatinine, waste products, it can be drugs, it can be even good stuff like vitamins. If you take 3 vitamin C pills, guess what? You only need like 5% of that. So the other 95% your kidneys are going to filter and get rid of. So that's vitamin C floating in the urine is considered a solute. So as the kidneys filter, we are regulating water volume. And if we're regulating water volume, what else are we regulating regarding the blood? If we're regulating water volume, we're regulating blood volume. And from the blood vessels chapter, and the heart chapter, you all know if we regulate blood volume, we're also regulating or helping regulate blood pressure. So doing a lot of cool, unique things all at the same time here with the kidneys. With those solutes, we are controlling the ion concentrations outside of our cells. Coming up, the next, we're going to be talking about acids and bases and fluid and electrolytes and all that stuff. You have a certain amount of ion concentrations inside your cells and outside your cells. Sodium being a really big ion outside of your cells. We control our sodium levels thanks to our kidneys. Sometimes you pee a lot of sodium out. Sometimes you don't pee any out. It just depends on your body's needs. We also balance our pH levels with the kidneys. So recall back to our first chapter, I believe, or one of the first chapters of this semester, about the pickiness of our blood pH. Our pH in our blood has to be a very small window. And the one that we talked about and that most textbooks say is your blood, at least in the arteries, has to be between 7.35 and 7.45. Now there are some anatomy instructors and physiologists that say that window's even shorter. It can be between 7.38 and 7.42. Regardless, though, it's a very small window. And if we go below that 7.35 towards acidity, we got all sorts of problems going on. We got heart issues, kidney issues, possible coma issues, really, really bad. If it goes above that 7.45, also really, really bad. Can have some breathing issues, seizure-like activity, just death, bad. Don't want it. We have to stay inside of that window. So the kidneys help do that. And we'll talk a little bit about that later on, but really all pH is, if you remember back to Anatomy and Physiology 1, all it is just how many hydrogen protons or hydrogen ions are found in the fluid or in your blood. So if our pH is getting too low, we're going to hold on to some of those hydrogen ions. Sorry, we're going to get rid of those, my bad. If we have too many hydrogen ions, which makes the pH drop, then we're going to pee that stuff out. If we have high pH, alkaline or basic pH, we're going to hold on to that stuff to lower it. So we're going to introduce buffers. We talked about bicarbonate earlier in the respiratory chapter, and we're going to introduce that as well again. So pH regulation. Other cool things that the kidneys do, the list goes on and on. Check it out. One of our favorite hormones from the blood chapter, EPO, erythropoietin. What does that help you do? That helps you make red blood cells, right? We have sensors inside of our kidneys that detect if we have low oxygen levels. If we have low oxygen levels, we make this hormone in the kidneys. The kidneys make this hormone called EPO. And then where does that EPO hormone get sent to? Well, what makes your red blood cells? Remember, that's your red bone marrow, right? Your red bone marrow is going to make more red blood cells, which is going to thicken your blood. It's going to change the viscosity of your blood. And if you change the viscosity of the blood and the resistance, you're going to be affecting the blood pressure as well. So, other cool thing, we have a hormone maker. We also have that really neat enzyme, renin, that we introduced in the blood vessels chapter. Remember, this is part of the Renin-Angiotensin-Aldosterone System. So the RAS or the RAM, depending on what we covered earlier in the book. So this is, I call it RAS. That's how I was always taught. System or mechanism, same thing. But this is going to be involving if we have low blood pressure. If we have low blood pressure, renin gets secreted, and then this whole enzyme protein interaction happens. We'll talk about that in great detail. We'll review it again. And eventually what that's going to do is increase your blood pressure from a systemic standpoint. We're going to get the hypothalamus, all sorts of things involved, adrenal glands, to raise your blood pressure. Because we don't want to be passing out, right? And we also don't want to have poor perfusion. We want to make sure oxygen and nutrients are getting to every cell in our body. We also make vitamin D. Well, we don't make it. We activate it. How about that? The kidneys. So remember, vitamin D comes from going out in the sunshine, right? It's got to be around 65 degrees or warmer Fahrenheit, and really just 15-20 minutes on your arms, face, legs, whatever. And that's really a good amount if you're fair-skinned. If you have darker skin, you got to go a little more exposure. You got, I don't know the exact number, maybe, 45 minutes. Or maybe it just has to be hotter out, 80 degrees. So you get a little bit more of that UV light. So that's what gets the ball rolling with those melanocytes and the melanin. And what ends up happening is that chemical that gets created is inactive. It doesn't really do anything. It's basically premature vitamin D. And then it gets processed by the liver, and it makes it kind of a teenager vitamin D, still not fully grown, but working on it. And then the kidneys is what actually activates it. And all the kidneys do is really they add a hydroxyl group. They add this OH to it. And that's what makes it fully functional vitamin D. And remember last semester why vitamin D was so important. It's for your bones, right? Well, a lot of different things, but bones is the main function. Calcium absorption has to do, kind of goes hand in hand with vitamin D. So if you want strong bones, you need both calcium and vitamin D in your system. So your kidneys help do that. Last thing, I mean the kidneys do more than this, but this is the last thing I have on this slide, is In severe situations, if we choose to not eat for a very long time, or we're stuck on a deserted island somewhere, we can actually go through something called gluconeogenesis in the kidneys. Now, what the heck is that? Well, in the metabolism nutrition chapter, you should have talked about that, right? Gluconeogenesis is when we make glucose, and neo means new, genesis means to make. So we're making new glucose from non-glucose products. Because if you're not eating, if you're starving yourself for a long time, you're not making sugar, you're not putting sugar in your body. So what we're doing here is we're breaking down fats in our body, and we're breaking down proteins, which would eventually be broken down into amino acids in our body. And guess what? You change that, you turn that into sugar. All you ketone lovers out there, yeah, good. Your body's full of ketone bodies long term. Probably not the best thing, but guess what? When it gets to the brain, once it gets to the cellular level, you turn those ketone bodies into sugar. And your kidneys actually, along with your liver, play a huge role with this if it's been several weeks of not eating any sugar products. So your body runs on sugar. It will make sugar no matter what. Pretty awesome. All right, so those are just a few of the things that your kidneys do. I hope you get an appreciation for the importance of it, right? If somebody is dying of cancer or renal failure, they get put on the transplant list, right, or potentially, and they die without that transplant. You can go through dialysis for years and years, but eventually you're going to need a new kidney. It's because the kidneys do so many things. So let's dive in and talk about some of the other organs of the urinary system, and then we'll come back to the kidney. All right, so once the kidneys do all their magic, once they filter the blood and actually make the urine, then we just got to get the urine out of our body, right? Because it's waste product. It's stuff that we don't want being built up. So what we're going to do is, you guys are really going to appreciate my art this chapter. Here's your kidney, here's your other kidney. What we're going to do is we are going to send it to our storage place. And our storage place is the bladder. That's the bladder, B for bladder there. And in order to get it there, we got to connect it to a tube. And those tubes are called ureters. So ureters in green. And then from the bladder, I think most of us have heard of this tube. From the bladder, whether you're male or female, you have a opening to the outside environment. That's called the urethra. And once you basically relax the bladder, you open up the sphincter, urine flows out, and you're peeing. So once again, we're going to talk about ureters, bladder, urethra, but at the very end, and it's very short. The beef of this chapter, what does all this magic, is the kidneys. As you can see in these definitions, what do these things do? Ureters, transport. It's just taking urine from A to B. Urethra, transports from B to C. Bladder, no big deal. Bladder's just a big bag. You kind of need it. I mean, it is important, but other than that, it's a big bag for holding urine. The kidneys is what's doing all the crazy stuff. So, really good picture here showing you the anatomy of a little bit of the urinary system. You can see the kidneys and their location. And we're looking at a posterior view because you can see the spine, right? So we're actually looking at the left side over here and the right side over here. And what you can notice is the ureters, once again in green, that leave the kind of middle central portion of the kidney and they head down towards the bladder. And the kidneys, the organs, they are actually very, very posterior. And this is a really good picture. I'm glad we have this because it is protected by those last couple floating ribs, or at least a little bit protected. And it's really, really close to your vertebrae. It's on either side of your spine. So this is very posterior. What we call this is retroperitoneal. So if you remember from the digestive system, that cavity holding in all of your guts, all of your intestines and stomach and omentums and mesenteries and all that stuff, that was called the peritoneum or the peritoneal cavity. When we say retroperitoneal, that means the kidneys are behind all that. So they are literally posterior to all of your guts. So in order to see this in a dissection, you would have to remove all of the digestive system, all of that dozens and dozens of feet of tube in order to see the kidneys. One more thing I want to point out before we move on to the next slide is on the right side of your body, you have a very, very large organ, the largest internal organ of your body, the liver. So, the liver takes up a big portion of this right upper quadrant. So if you notice in this picture, not exactly the best illustration, but if I was to take the top of this kidney and just kind of draw a straight-ish line, you'll notice that the left kidney is a little higher than the right kidney. And that is normal anatomy, that is okay. And mainly it's because that liver kind of pushes down on that right kidney a little bit. All right, moving on. Let's take a look at the external anatomy before diving in and actually cutting the kidney open and looking at what's inside. So as I mentioned before, the kidneys are what we call retroperitoneal, so they're behind all of that digestive viscera, all those organs. As we mentioned on the previous slide, the left one is a little more higher or superior than the right one, mainly because that liver's in the way on the right side. And on top of the kidneys, we have these little party hats called the adrenal glands. So here are my kidneys. One's a little bigger than the other. But on top of each kidney, we have these triangular looking organs. Those are the adrenal glands. And it's very similar to the thyroid and the parathyroid glands. Even though they're right next to each other, even though they're touching each other, they are completely separate organs, totally different. The adrenal gland is an endocrine gland, so it releases a lot of different types of hormones. Kidneys only release 1 or 2 hormones. So kidneys mainly going to be filtering blood, making urine. Adrenal gland totally separate, but they are the adrenal gland sitting right on top of the kidneys. So on the lateral aspect of the kidney, it has a convex surface. So let's draw a mid-sagittal line here in green in the middle. This would be our belly button, pubic bone area, right down the middle of the body. So on the lateral side is where we see this convex shape, just meaning basically, if you remember the stomach, we had a greater curvature and a lesser curvature. The greater curve, the bigger curve, is going to be on the lateral side. And therefore, the concave right here will be more medially. And that's where we're going to see the hilum. And the hilum is just basically where we have all the stuff going in and out of the kidney, just like we saw in the lungs. Right? In the lung hilum, we have the pulmonary artery and pulmonary vein and bronchial tubes and all that. It's the same thing here. So we're going to have all the blood vessels, as you can see. Let me clear some of this out for you. There we go. So you can see the blood vessels. We're also going to have lymphatic vessels, right? We need to fight disease in the kidney area. We're going to have your nerves. We're also going to have those ureters that are going to drain the kidneys to go to the bladder as well. So on the medial side, that is where the hilum is. I'll show you a picture on the next slide to give you an even better look on this. Okay. So just to kind of reiterate the hilum, it's going to be this area right here on the inside of the medial portion. And you can see this tube that I'm highlighting in green, that is the ureter. You can also see it in this bigger picture right here. And then it'll eventually go down to the bladder. All right, so on the outside of the kidney, what we're looking at here are 3 layers supporting and protecting the kidney. Kidneys are really important. Unfortunately, we can get some really nasty infections in the kidneys. We can get urinary tract infections that work their way up to the kidneys. We can get all sorts of pyelonephritis, glomerulonephritis. We can get all sorts of kidney stones, all sorts of bad issues with our kidneys. The good news is we do have lymphatic tissue, and we are able to kill these things eventually, sometimes with the help of antibiotics. But we want to make sure that just like any other organ, this organ is isolated. It does have its own little bubble surrounding it. So we have several different layers protecting the kidney. The first layer that's actually protecting the entire organ itself is something called the fibrous capsule. So what I'm doing here is I'm working deep to superficial. So the fibrous capsule is the deepest out of these three. This is actually touching the kidney itself. And as I just mentioned, it prevents spread of infection, right? We don't want stuff getting into the kidney. We also don't want stuff, bad stuff, leaking out of the kidney and affecting all of the organs, the peritoneal organs and the digestive organs next to that area. So we want to keep things isolated. Surrounding the fibrous capsule, you have a lot of fat on the kidney, and we call this perirenal fat, peri meaning around. Now this is really, really, really important. We've talked about the importance of fat last semester, this semester, but specifically the heart and the kidneys need a lot of fat around them. They operate at different temperatures. So in order for the kidney to work optimally, we need a little bit of fat. It's also going to protect it, right? If you remember that picture 2 slides previous to this one, the floating ribs do protect a little bit of the kidney, but not the whole thing. There is a little exposure. So if somebody sucker punches you or hits you in the lower back, you do want a little bit of protection, and that fat does serve as a cushion. And then last but not least, we have the renal fascia, and that's the most superficial. That's kind of outside all of the capsule and the fat capsule. And you can take a look at what it looks like here. Just kind of wrapping around, just kind of like this big network of connective tissue. And basically it just, same thing as connected, it just supports it, just protects it, and just makes sure that it's isolated. So make sure you know these 3 layers going from deep to superficial or superficial to deep. If we were to actually like cut into a kidney, like doing surgery, if we cut into somebody's lower back, we would first hit the fascia because that's the most superficial. And then we would hit the capsule, the fat capsule, and then the fibrous capsule. So this would be superficial to deep, obviously. All right, so that's the external anatomy of the kidney, what it looks like on the outside. Let's get to the fun stuff. The internal anatomy of the kidney gets really cool. But we need to have an understanding of the anatomy before we get to the physiology, because the physiology gets insane, just gets nuts. All right, so 3 parts to the internal kidney. And obviously on this slide, you can only see 2. We're going to cover the 3rd one on the next slide. But let me draw my version of a kidney. There we go, little kidney bean. And what we have is a cortex and a medulla, just like most organs, right? You have a thyroid cortex, thyroid medulla, adrenal cortex, adrenal medulla. Even in the bones, last semester we talked about the cortex of the bone, and then the medulla or the medullary part of the bone is the inside. So it's the same thing here. The rules are the same. What we're going to have is we're going to kind of have this separation, if you will, like this. And this outer portion that I'm highlighting in black, that's going to be our cortex. And then the inside, or the deeper part, the more medial part, is going to be our renal medulla. And inside the medulla, we're going to have these really cool triangular looking things, and we call them renal pyramids. So just a few, while I'm drawing this, a few root words. Anytime you see the word renal, that always refers to kidney. Anytime you see the word nephro or prefix nephro, that's always going to refer to the kidney as well, or a specific part of the kidney. So we're learning renal anatomy right now, anatomy of the kidney. Okay, and the renal pyramids, these purple triangles that I just drew, that's where we're actually going to be forming the urine. What we call pre-urine, or what we call specifically filtrate. And then we're literally going to dump the urine at the edge of these pyramids. So in green, at the very tip of these pyramids is where the urine is actually going to be dumped and collected. And then we're going to have these tubes that drain, kind of like these funnels that drain. And they're going to run together, and then we're going to have the 3rd part of our internal gross anatomy called the renal pelvis, and I'll show you that on the next slide. But basically what we're doing is we're starting the process of filtering the blood and making the urine on the outside in the cortex, and then we're going to drain it through those pyramids, through those triangles, and then we're going to drain it through this funneling system, and eventually it's going to leave the kidney through the ureter and go to the bladder. So that's kind of the order of making urine and then getting urine out of the kidney, going from outside to inside. Those tips at the edge of the medulla, those are called renal papilla or papillae, plural. And what it means is it literally translates into nipple, and that's kind of exactly what it is. It's just several openings that look like tiny little nipple openings, and that is where the urine is actually draining into that funnel that I mentioned. One more thing that I want to show you on this slide is the renal columns. And as you can see, the renal columns is what separates the renal pyramids, and they're extensions of the cortical tissue. So the cortex in the kidney is a little weird. It does extend between the triangles like this. And right there, basically what's going on in the renal columns is we're just going to have blood flow. We're going to have arteries and veins going back and forth, supplying all of the little worker bees inside of the kidney that we're going to find out about shortly. All right, so as we're looking at this picture, first let's get our orientation right. What we're looking at is the inside of the kidney. So what we're doing is we're taking a frontal cut or a coronal cut of the kidney and cutting it in half, so we have an anterior and a posterior half, and then we're looking at the inside part. So that's what you're seeing here. Just a little review of some of the structures that I talked about in the previous slide real quick. The tissue that I'm coloring in black right now, this is all the renal cortex. And remember, the renal cortex does extend between those triangle, those pyramid-looking things. So that's called the renal columns that I'm drawing kind of in the medulla right there. The renal medulla is pretty much everywhere where you have the pyramids, and you can see the pyramids in purple. And that's why they call them pyramids. They're like these little triangular-looking structures. And at the very, very tip of the pyramids, we have the papillae, and the papillae, let me clear all this out and I'll show you. The papillae are just what's dumping into this funnel-like system right here. So the papillae would just be the tips. Now, as I mentioned, the tips dump into this funnel system, and what this funnel system is, at each renal papilla, we have our own unique funnel system, and what we call that is a minor calyx, or plural calyces. So each pyramid has one minor calyx. So if you look in this picture, we have 1, 2, 3, 4, 5. We have 6 pyramids, and therefore we're going to have 6 minor calyces. Then what happens is we're starting to drain the urine towards the bladder, so the minor calyces come together in some areas. As you can see that this minor calyx and this minor calyx form a bigger unit right there. That's called the major calyces. And then when you get a whole bunch of major calyces together, you get this big knot-looking thing. And it's in this picture, it's not the best because the renal artery vein and the nerves are blocking it. But this big knot right here, where all the major calyces come together, that's the third part of the internal anatomy. It's the renal pelvis, is what we call it, the renal pelvis. It's just a collection of all these funnels, and then from the renal pelvis, we're going to take that urine and actually leave the kidney, and we're going to go down this long, slender tube, and once again, that tube leaving the kidney, going to the bladder, is called the ureter. And we're going to cover blood vessels in just a little bit, and I've covered everything else. Cool. All right, let's keep moving. So as you can see here, the third part, as I mentioned, the renal pelvis, and all the renal pelvis is a collection of the major calyces. And all the major calyces is a collection of the minor calyces. So you need to make sure at the end of this chapter you can take a drop of urine, or what we're going to call filtrate, a drop of filtrate, and trace it through the entire kidney. Now, by the time it's leaving the renal pyramid, it is urine at that point. So for urine, it's really, really simple, but we're going to learn about all the pre-urine and how we filter the blood in just a little bit and add a lot more anatomy. But for right now, what you need to know is the renal pyramid is what's draining it. Remember the little opening, the nipple opening is called a papilla, or papillae plural. The papillae dump into the minor calyx. Minor calyces form together to form the major. A bunch of major calyces come together to form the renal pelvis. And then the renal pelvis dumps into the ureter, and you have a ureter on the left and a ureter on the right that both dump into your bladder. And then through the urethra, you're going to eventually urinate the urine out. So that is the flow of urine in a nutshell. Let's move on to the next slide, and we'll cover blood flow through the kidney. It gets a little more complicated there. Renal blood flow. So before we dive into the details here, I want to give you two things so you don't freak out. Number one, we're going to spend a long time on this slide, and I'm going to show you the blood flow and the orientation of everything. In case you're not a big visual learner and you're more of a logistical, just black and white learner, everything that we're going to talk about on this slide for the most part is going to be on the next slide in black and white letters showing you A to B to B to C to C to D. Okay. Second, on this picture, you see the kidneys on the left, and we have this weird, crazy tube-looking thing with a bunch of blood vessels surrounding it on the right. What that structure is on the right is the nephron. And the nephron is the functional unit of our kidneys. What does that mean? That means your kidneys run on this stuff. This is what is actually filtering the blood. This is what's actually making the urine. This is what's adjusting the pH and the blood volume and the blood pressure and doing all those crazy things that the kidneys do. So without these, you die. Very similar to the neurons in your brain. Without neurons, your brain doesn't work. Or the alveoli in your lungs. Without alveoli, your air sacs, your lungs don't work. So the nephron, functional unit of the kidney. This is the worker of the kidney. Now, where these things are located, as you can see, maybe you can see in the, based on the picture, they're located, they start in the cortex area. I'll draw it out here in purple. They start in the cortex, and then some of these tubes kind of dip into the renal pyramid area. Not all, well, they all do, but I'll get more detailed in a bit. So that's going to become important because we're going to, when we talk about blood flow, we are going to use this nephron as part of our blood flow. Real quick summary or real quick review of blood flow through the body. Remember, everything starts once the heart pumps out through the aorta. The aorta is an artery, so everything leaving or branching from the aorta is an artery. From arteries, it goes to arterioles, right? I'm just going to put artoles to save time. From arterioles, then we get the magic workers, right? The things actually doing the exchange. We call those the capillaries. And then hopefully you're filling the rest of this in for me, right? Capillaries lead to the small veins. We call those venules. I'll just put V-E-N for venules. And then the venules lead to the veins, right? And then we're going to go back to the heart, to the lungs, to the heart, and then do it all over again. That's all we're doing here. So we're going to trace it from the aorta. We're going to trace it through the kidney to the capillaries, and then we're going to come back to the kidneys and go back to the heart. That's all we're doing. All right. So let's start at the kind of bottom left of the page. Here, the renal artery. Of course, remember, all arteries come from the aorta. There we go. So the aorta goes down into the abdomen. We call that the descending aorta or the abdominal aorta, and it branches off into a left and right renal artery. And the renal artery is just this big artery that's kind of entering the hilum. And then as soon as the renal artery gets actually inside the kidney, it immediately splits into several different segments. Like that. And that kind of makes sense that the next artery, all those segmented arteries are called segmental arteries. Cool. From there, what happens is these segmental arteries continue going through the renal columns. They go through this cortex kind of between the pyramids, as I'm drawing. And as they're going between the pyramids, they change their name. They are now called interlobar arteries. So the renal artery segments and the segmental arteries, and then the segmental arteries continue towards the cortex, and they're called interlobar arteries. From there, our next step is these arteries kind of arch or make this curve shape over the base of the renal pyramid. So let me try to show that to you. So once we're near going between the pyramids, you can see how this artery is kind of arching around the pyramids, arching around the pyramid, around the pyramid. So what we call that makes sense. Once again, we don't try to confuse you too much with the naming of the vessels here. That's called the arcuate artery. It's arcing. It's making this kind of arch-looking shape. But notice the significance of the arcuate artery. It also differentiates between the cortex and the medulla. So anywhere superficial to the arcuate artery, that's going to be cortex. Anywhere deep is going to be your renal pyramids, pretty much. That's going to be the medulla. So once we start diving into the real specific parts of how we filter and move stuff around, you're going to see the arcuate artery and the arcuate vein for that matter. Okay, from there, the arcuate artery starts branching out into the cortex, and it makes this kind of radial shape. So here's our arch that I'm drawing out here now. There's our arch. And then it just kind of branches, kind of like a rays on a sun, I guess, just all these sun rays. And what we call those are the cortical radiate arteries. Cortical meaning cortex, radiate, radiating around that artery. Now in some textbooks and some other sources, this is also called the interlobular artery, not to be confused with the interlobar artery. But I always learned it. I was always taught this. Cortical radiate, it makes sense, right? It's radiating like a sun. So you can see them all down here, just all these red arteries just kind of going crazy everywhere. Now, there is a reason for that. All those crazy radiating arteries are going towards your worker bees, towards your nephrons. You have 1 million nephrons in each kidney. So you have 2 million nephrons in your body, approximately, if you have 2 healthy kidneys. So that's why you can still live without a kidney. You can live with one. You got to be careful with diet and exercise and stuff like that. But if you have 1 million nephrons, you'll be okay for the most part. You can live a somewhat normal life. As the cortical radiate arteries start moving towards these nephrons, we get smaller. So we are no longer talking about an artery, we're talking about a mini artery. And what we call those, once again, are arterioles. Now, check this out though. As we enter from a cortical radiate artery to the afferent arteriole, remember last semester, we've seen this word before, afferent. I always said afferent, right? Enunciate the A, because there's another one called efferent. And that sounds kind of similar, afferent, efferent, right? So we have afferent and efferent. Afferent was the one arriving towards something, and efferent was the one leaving or exiting towards something. We use this in the nervous system. It's the same thing here. The afferent arteriole is what's going towards this big blob of capillaries in the nephron. And then the efferent arteriole is what's leaving the nephron, or the part of the nephron. So this is kind of weird. We have the afferent arteriole, and then we have this weird thing that I'm highlighting in purple called the glomerulus. You're going to hear me say that word a lot. This is one set of capillaries. So what we're doing is we're going arteries to arterioles to capillaries. Awesome. That's how we always learned it, right? But then guess what? From capillaries, we have a second mini artery, which is really, really weird. Kind of like the liver, right? The blood supply of the liver. We had the hepatic portal vein, and we had those 2 capillary beds, giving the liver extra time to clean things. Same thing here. We're going to have 2 types of capillaries. So from the glomerulus, we're going to go back to little arteriole, our efferent, and we're going to leave, and we're going to send that to another set of capillaries. Crazy, crazy, I know. That's called the peritubular capillaries. Once again, peri means around. So it's all these capillaries around the tubes of the nephron. So it's all these little squiggly red things you see in the picture. Now, sometimes if these capillaries get really long and skinny around this big loop, sometimes that's called the vasa recta. Vasa meaning vessel, recta meaning straight up and down. And I'll show that to you on the next slide, but just FYI. Okay, how we feeling? So once we get through those capillaries, what's going to happen is we're going to go through this little tiny thing. This is going to be our venule. And to be honest with you, I don't know the name of the venule. We'll just call it the renal venule. It's just a small vein. It probably doesn't even have a name because it's so small. Just like we don't usually name capillaries, right? Capillaries are just capillaries. Then from there, we're just going to work our way backwards. Just like we did with arteries and veins and previously in the semester, same thing. There's only going to be one weird exception. So let me clear some of this out. Once we are returning back through the venous blood supply, we're going to hit the cortical radiate veins. And then we're going to go to the arcuate vein, just working our way back out of the kidney. Then we're going to go through the interlobar vein that follows. All these are right next to the arteries, their respective arteries. And then we're going to go to the renal vein. So notice something real quick. There is no segmental vein. We went from renal artery to segmental artery to interlobar artery. With the veins, it doesn't segment. It just goes straight from the lobes to the vein as fast as possible. And then from the renal vein, we know it's going to go to the inferior vena cava. And the inferior vena cava is going to take it back to that right atrium in the heart. All right. So for you visual learners, hopefully that'll help you. For you, I don't know, I guess not so visual learners, let's move on to the next slide and I'll show you what I just discussed. Okay, so here's the order you need to know in order for you. As we mentioned, starts with the aorta, goes to the renal, segmental, interlobar, arcuate, and then I did put the other name for you here. The cortical radiates are also called the interlobular, not to be confused with the interlobar. And then we go to the afferent arteriole and then our first capillary network called the glomerulus, and then the efferent arteriole. And then we have our second capillary network. And once again, if the capillaries wrap around that real small skinny loop looking thing, we're going to call that the Loop of Henle later. We call those capillaries vasa recta, just up and down capillaries. And then we just work our way backwards. We go cortical radiate or interlobular veins, arcuate vein, interlobar vein. Remember, there's no segmental vein, renal vein, and then the IVC. So make sure you understand and know the blood flow through the kidney. So as all that blood is pouring through the kidney, what's happening is it's got to go to the nephron, and these two capillary networks, the glomerulus and these peritubular capillaries, that's where the magic's happening. That's where we're filtering the blood, we're reabsorbing stuff, we're secreting bad stuff. This is where we're cleaning the blood and making your urine. It's those two capillary networks that we're going to go in great detail in just a bit. All right, with the nephrons, once again, this is the functional unit and structural unit. Most of your kidney, at least in the cortex and the renal pyramids, is just a bunch of tubes. These are called nephrons, and you can't live without them. Good news is you got about 1 million of them, or more than 1 million per kidney. So that's what's filtering your urine, filtering your blood, cleaning your blood, making urine. And there are two main parts to the nephron. We have something called the renal corpuscle. And what the renal corpuscle is this big ball-looking network that I'm circling in black. That's the corpuscle. And then everything else is called the renal tubules, and those are just the tubes. So all of this crazy mess that's in tubes are the renal tubules. And you can see once again the blood flow going in. Great picture showing you the interlobular, this is the cortical radiate artery here, cortical radiate artery, and then it goes to the arterial, and then the other arterial, and then the capillary network. And once again, okay, I was right, it's just called a venule. Cool, there isn't a specific name to it. And then it goes just back down, eventually back to the heart. All right, the renal corpuscle is first. So the renal corpuscle also consists of two parts. Number one, you've already been exposed to. This is called the glomerulus, and all this is a huge mess of capillaries. In your book or your notes, it says a tuft. What that just means is a big yarn ball, hot mess of capillaries going everywhere, and a lot of capillaries. And these are composed of fenestrated endothelium. What the heck does that mean? Fenestrated is just where we have a lot of holes in the capillaries, so these things are extremely leaky, which is what we want, right? We want them to be leaky because we're filtering the blood, we're cleaning the blood. If we don't have any leaking anywhere, the toxins that build up in your blood are never going to be able to get out. So there is a purpose to that anatomy right there. We want that fenestration. I'll show you a picture on the next slide. So that's the capillaries. The thing surrounding the capillaries, that ball-looking structure, is called the glomerular capsule, also known as the Bowman's capsule. You'll hear me say Bowman's capsule pretty much for the rest of this lecture, but just in case, don't freak out on a test question or anything if it says glomerular capsule. It's the same thing. But Bowman's capsule is the thing surrounding it. So let me draw us our, here's all our big mess, yarn ball, crazy thing of capillaries. And then Bowman's capsule is this kind of balloon-looking thing that kind of swallows the capillary network. And then here is where you have the afferent arteriole coming into the glomerulus, and then there's the efferent arteriole leaving the glomerulus. So the big thing in purple is the Bowman's capsule. Now, as you can see, the Bowman's capsule does have two layers, what I just drew for you. We have a visceral layer, the layer that's actually touching, or pretty much touching, not in, this picture's not the greatest, but it's pretty much touching the capillaries. That's going to be in green. And then the outside layer that's not touching anything, in gold, that's going to be our parietal layer, just like every other organ cavity that we've talked about so far these last 2 semesters. All right, now take a look at the epithelium though with the Bowman's capsule. It's kind of weird. The parietal layer is simple squamous. Now, this is a very weird exception because usually with that parietal layer we want protection, separating the heart from the lungs, separating the digestive organs from the stuff around the digestive organs. We want protection in that parietal layer. Here, we're not concerned about protection. What we're concerned about is filtering things. So from this parietal layer, what we're going to have is we're going to have those tubes, those crazy tubules, the second part of the nephron. So what we need to do is as we're taking the junk out of this capillary network, it's going to be pushed or forced into this capsule, and then we're going to push it into the tubes. And that's where we're going to start cleaning the blood. Well, at this point, it's no longer blood. It's called filtrate because all the cells stay in the blood, and we're just really taking out the plasma is what we're taking out. So at this point, you can say it's plasma, or more specifically, it's filtrate. So there is a purpose. Everything's got a purpose, structure and function. There is a reason why this is simple squamous. Remember, the purpose of simple squamous is diffusion. It's letting things in, letting things out. We want that to happen in the nephron. We want all of that blood to eventually get forced into this capsule. The visceral layer, as you can see in the bullet points, clings to the glomerular capillaries of the glomerulus. Now, once again, though, there are little tiny slits in this area. And these slits, what's actually covering the glomerulus is the cells called podocytes. And these podocytes are these they look like astrocytes kind of. They're these weird, are y'all good if I clear this capsule out, this picture? Hope so. What a podocyte is this weird alien octopus looking thing where you got the kind of like a cell body, and then you have all these tentacle feet looking things. And the feet are called pedicels. And so if anybody's ever been to a podiatrist, maybe you've heard some of these prefixes before. Pod means foot, and ped also means foot, right? So podocytes are cells that have feet, and then the actual feet are called pedicels. And what they're doing is they're creating these very, very small spaces between the visceral layer and the glomerulus, the capillaries, so stuff can leak out. Let me repeat that. The visceral layer is actually touching the capillaries. And we have these little tiny slits to allow things to leak out or to be forced out. Once again, our main job here is we are filtering the blood. So we want things to leak. So we're going to have these cells that create, and these cells, to be more specific, they kind of overlap each other. So we have, let me draw like 3 or 4 podocytes, and all of their legs kind of overlap or intertwingle or interdangle. Intertwine is the word. There we go. And what ends up happening is we have these little tiny slits where big stuff can't get through. So these blue things are the slits, and your big red blood cells can't get through. Your big white blood cells can't get through. Your platelets, big proteins like albumin, can't get through. And that's good because we kind of want that to stay in the blood, right? We want our red blood cells and our white blood cells staying in the blood. So what's really getting through is all the tiny solute stuff. So these are your vitamins, your minerals, this is your glucose, a lot of this is water, tiny proteins that can fit, a lot of ions, electrolytes, those kind of things is what's leaking through these little slits. So let's move on to the next slide and I'll show you a picture. So great illustration of the fenestrated capillaries. Fenestrations are just the holes you can see in the capillaries. We just have all of these holes in the endothelium, which just allows these really small particles to leak through the glomerulus. And then on the next slide, I'm going to show you what in the heck I was trying to draw with those podocytes and those pedicels. There we go. All right, so take a look at the picture on the right for me. What we have is we have this red blood vessel, that's a capillary, and then on top of it are those cells, those podocytes. And then if you look at the left, it's the zoomed in version. What we have are all these little feet what's that word that I keep messing up? Intertwined? Yeah, intertwined. They're just all kind of overlapping one another. There we go. And all these little tiny slits is what allows that small stuff to leak through, but the big stuff stays inside. So once again, the important red blood cells, white blood cells, platelets, big proteins, that can't fit through those filtration slits. So that's just going to return right back to the bloodstream. That's going to go through the efferent arteriole to the capillaries, and then to the venules, and then to the veins back to the heart. So you don't have red blood cells, white blood cells, platelets in your urine. If you do, you are sick. You need to go to the doctor. Okay, if you have blood in the urine, that's bad. If you have white blood cells in the urine, you have a kidney infection, or at least a UTI. You have something wrong. They're too big to normally fit through these slits. So once again, the stuff going through these little tiny filtration sites is the junk we're going to be getting rid of, or we're just filtering. We're just cleaning it, and then we're going to put it right back in the bloodstream. So certain things like vitamins, like sugar, we want that in the bloodstream, right? But let's clean it in case there's junk attached to it. So we're going to push it through these little slits, and then we have processes to clean them. And then the junk, the waste products like urea or uric acid or creatinine or all those things, that's what we're going to not put back in the bloodstream. Eventually, hopefully that stuff becomes our urine. So we'll talk more about that. But I wanted to give you an illustration of these cells and their little feet. All right, so we talked about the renal corpuscle, right? That's the Bowman's capsule surrounding the capillary network that we call the glomerulus. Now we're moving on to the second part of the nephron called the renal tubules. And you have all sorts of different cool little weird tube-looking things. And then all of the tubes collect into this thing called the collecting duct. So let's get our orientation right before I dive into what the heck we're talking about. Let's play follow the maze. Right, when we were kids, we like to draw at the restaurants or whatever. So if we start here at the glomerulus and the Bowman's capsule, we're going to push all those waste products and the filtrate into this first tube. This first tube that I'm tracing right now is called the proximal convoluted tubule. So that's that part in black. Proximal meaning it's attached, it's the first part, right? It's the first part of this tube. Convoluted means it's convoluted, it's crazy, it's winding, twisting, turning, going back and forth everywhere. So let's continue down the maze. So as we go down the proximal convoluted tubule, we make this big U-shaped looking thing. This big U-shape is called, in your PowerPoint notes, is the nephron loop. We got to change that. That drives me nuts. This thing is called the Loop of Henle. Loop of Henle. It's this big old loop. So we have a descending part of the Loop of Henle, and then we have an ascending part. And as we go up to the ascending part, we eventually get to our next convoluted tubule that I'm currently tracing. This is called the distal convoluted tubule. And then what happens is this distal convoluted tubule meets up with a whole bunch of other distal convoluted tubules throughout the cortex of the kidney. Now remember, how many nephrons do we have in one kidney? 1 million, actually more than 1 million. I don't know the exact amount, but more than 1 million, a boatload, right? So what this big long tube on the very right is, that I just highlighted in green, this is called the collecting duct. And at this point, it's pretty much urine. All throughout the tubes, the tubules, the proximal convoluted tubule, the loop of Henle, and the distal convoluted tubule, it's pre-urine, it's pre-pee. It's not truly urine yet. We're still cleaning and filtering stuff with that plasma. It's called filtrate at that point. Once we get into this collecting duct, it's pretty much urine. But what happens is this distal convoluted tubule goes into the collecting duct, and so does a distal convoluted tubule from another nephron, and another nephron, and another nephron. And you have 6, 8, 15 different distal convoluted tubules from 15 different nephrons, all draining into one collecting duct. Now, take a look at where the collecting duct goes at the very bottom of the notes. The distal convoluted tubules drain into the collecting duct, which fuse into the papillae, the renal papillae in the pyramids. These are the nipples, the openings. So all the collecting ducts drain into the openings, and then we're going to get rid of the urine. So they go to the minor calyx. The minor calyces make a major calyx. Major calyces go to the renal pelvis, and then you know the rest. Renal pelvis goes to the ureter, then the bladder, and then the urethra. So this is the formation of urine. So now, going back to your notes, when we first talked about the formation, we said starts in the kidney, and then it goes to the calyx, blah, blah, blah. Now you can add even more detail, which I want you to know. It starts in the nephron. So let me clear this out. It starts in the Bowman's capsule and glomerulus, and then this filtrate, this pre-urine, goes through the PCT, which is what we abbreviate the proximal convoluted tubule as, goes through the loop of Henle, and then it goes through the DCT. And then it goes through the collecting duct, and then it goes to the papillae, the minor calyx, major calyx, pelvis, ureter, bladder, urethra. All right, so now you really know the formation, and well, not the formation yet, but you know the flow of urine throughout the entire kidney. So definitely need you to know that. Now, what we're going to get to in just a little bit is the epithelial tissues and throughout these tubes do change. They do get a little different. Sometimes we're going to let certain things in and not other things. And that's how we're going to filter this filtrate or this pre-urine. So here's the buckle up part, because we're about to just go into more awesome detail. The kidneys are really cool, but it gets crazy. All right. Okay, one note to make real quick. All these drawings of the nephron that we've been showing you, the ones that I drew and the one that is on this picture, they're actually anatomically incorrect. The distal convoluted tubule actually wraps around right near that Bowman's capsule. So I'm going to draw you a new one on the next slide. But I'm just this is a good picture to show you the flow and how the filtrate goes through these things. But I'm going to change the anatomy of it on the next slide for you. Okay. All right. So how does the blood actually get cleaned? How do we move around and manipulate this filtrate? How do we make our pee? It's the nephron. And as you can see, we got a lot of cool things going on here, stuff moving in and out. Now, with this picture, let's identify our terms first. Here you would have the glomerulus inside the Bowman's capsule, right? So these two things together, we call that the renal corpuscle. This first little winding bit of tube we call the proximal convoluted tubule. We have our loop of Henle down here. And then we have the distal convoluted tubule. I'll put DCT. And then we have our collecting duct where a bunch of other DCTs are going to be joining together. Right? Do you agree with that? All right, so that's the anatomy of the nephron. Now, to put this in perspective, Okay, so also what we have to understand and appreciate is this nephron is surrounded by blood flow. We have those peritubular capillaries and that vasa recta, which is a type of peritubular capillary. We have these things everywhere. So I'm just going to circle, it's just red everywhere. There's blood flow all over this thing, surrounding it, right? So as we move stuff back and forth, we're moving it between the bloodstream and the tubules. Now there is a little space between them. There is some interstitial fluid, interstitial space. But as soon as it leaves one or the other, by diffusion purposes, for the most part, it just goes either to the tube or the blood. All right, so let's take a look at what actually is moving throughout the nephron. In the proximal convoluted tubule, what's happening is all of these things are getting what we call reabsorbed by the bloodstream. So whenever you see an arrow leaving the tube, that's called reabsorption. I'll have this on the slide coming up. But we are reabsorbing it or bringing it back into the blood. So what we did was we filtered it through this glomerulus, we filtered it through the capillaries, and then we said, hey, we want this stuff. We want to hold on to this for a little bit. So take a look at all the things that are being brought right back into the blood. As soon as we go through the Bowman's capsule and the glomerulus, we just put this stuff right back in the bloodstream, because a lot of this is important. You look, glucose, your brain and red blood cells run on glucose. You need that. Amino acids. Why would you eat protein if you just pee it all out, right? We want to hold on to some of that stuff. It helps us build tissue, helps us build muscle and protein. Proteins, small proteins at least. Vitamins, right? You want your vitamins. We do have some weird ones. We have lactate and urea and uric acid. And generally speaking, a lot of folks would call those waste products. I would agree with them for the most part. But we do have to worry about concentration gradients here. We don't want to throw everything into the tube all at once. We can manipulate water and sodium and other concentrations by holding on to some of this stuff in the bloodstream. As you'll see later on, we will eventually get rid of some of this stuff. On the right, you see a bunch of ions and water, right? We got sodium, potassium, calcium. Very important. We want that stuff in our bloodstream, right? Sodium and potassium helps your muscles go. It helps your brain send action potentials, helps your heart pump. Calcium helps your heart pump. It's the main ingredient of your bones. We want that stuff coming back to the blood. Once we clean it, come immediately back. Magnesium, also very important. Chlorine, another good important electrolyte. We have bicarbonate. You can see HCO3. We talked about that in the lungs. That's our big buffer, right? As we're manipulating pH, we need that 7.35 to 7.45. Bicarb is a big contributor to that. And then we have water, right? And water, we should probably shouldn't put water last, but we are bringing water back into the bloodstream because we don't want to dehydrate ourselves unless we need to get rid of water because we drank too much water. So what I want you to know is all of this stuff is being reabsorbed back into the bloodstream in the PCT, and that right there is about 70% of the filtrate. I'm going to put a 70 right here. So all of the fluid, and I'm going to tell you numbers in a little bit, and it's going to blow your mind, but out of all of the fluid that's getting filtered by the glomerulus and the Bowman's capsule and then coming into the PCT, 70% of it right away gets sucked right back into the bloodstream. So we're only dealing with 30% left of the filtrate. As we work it down into the PCT, you can see this next bubble with the star next to it. Notice we're starting to pour stuff from the bloodstream into the renal tubules here. And you can see this is where we're getting some of the waste products. You can see urea. Once we've figured out, okay, the blood needs this amount of urea, not this much, all right, but, kind of just homeostatic ranges, not too much, not too little. Uric acid, creatinine. Creatinine's a normal breakdown of protein, especially muscle. So this is our big indicator. It's a different one now, but sometimes it can be an indicator of kidney function by measuring how much creatinine you have in your blood. If you have too much creatinine in your blood, that means your kidneys aren't cleaning it, and that means you could be entering kidney failure, kidney issues. But recently we're using a different protein now in blood tests. Drugs, any type of drug that your body's trying to get rid of. You name it, your kidneys are trying to handle it, get that stuff out of your body. Hydrogen protons. Remember, the more hydrogen protons you have, the more acidic your pH is. So if we are too acidic, we're definitely going to want to kick that stuff out of there and get it into the tubes, out of the bloodstream into the tubes, so we can put it in the urine. But if we're too basic, we'll actually do the opposite. We'll actually spit hydrogen ions into the bloodstream to balance that. And then we have ammonia, and ammonia is really poisonous. That's really toxic. pH of I think 12 or 13. That'll kill you if that builds up. And that's just a breakdown of protein. So the more protein you eat, especially from animal products, you're going to have a more ammonia buildup in your urine. And hopefully your kidneys are working and you just pee it out, right? So people who are big meat eaters, their urine may be a little more stinky, a little more yellow. It's because you have a more ammonia in your urine because you have more protein breakdown. That's all. Folks who don't eat a lot of protein won't have as much ammonia. Their pee won't smell as bad. All right, moving right along. As we move through the PCT, we go to the Loop of Henle. Check out the first thing that happens with the Loop of Henle as we're going down. We're bringing more water back into the blood. You can say blood. Really what we're doing is interstitial fluid, the space. I'll talk about that later. And we're dumping more waste product, more urea, into the tube. Now, as we're going up the Loop of Henle, what we can do is we can also absorb a few more electrolytes, sodium, potassium, and chlorine. Now, depending on our body's needs, if we're overhydrated or dehydrated, we can flip these arrows. So if we're overhydrated, water is actually going to be moving into the tubes. And, well, it depends on how much, but the salts can flip as well. If we're dehydrated, we're going to want to hold on to everything. We're going to want to hold on to those electrolytes, which are going to hold on to the water as well. Moving right along the loop of Henle, we get to the DCT. You can see more stuff leaving. Water, bicarb, chlorine, sodium. And then as we get to the collecting duct, we're dumping more waste products from the bloodstream. Hydrogen ions, potassium, ammonia. I'll talk about why potassium later on. There's going to be a hormone involved. Because you can see in the loop of Henle, we sucked out potassium into the bloodstream. And then here it's leaving the bloodstream, going into the tubes. Kind of counterintuitive, right? Or contradicting, but there is a reason for it. And then even in the collecting duct, we can make last-second changes. So if we're dehydrated, we can take water from the tube and put it in the bloodstream. If we're overhydrated, if we drink too much water, or we don't have enough electrolytes, and we need to balance that out through osmosis, we can move water into the collecting duct and pee that stuff out, right? So even if you drink a lot of water, say you just drank 2 bottles of water in the last 5 minutes, yes, your body needs water, but to one point, you just put too much water in the body, so that's going to affect blood volume, which could raise your blood pressure, so your body doesn't want that. But 2, you also just drowned out all your electrolytes, or at least you kind of made the electrolyte concentration less, and that's going to affect cellular function in the body. So in order to fix that, you can either A, add more electrolytes to your body after drinking 2 bottles of water, or B, what's easier is just get rid of the water, just pee out the water. So for those of you who do that, who just chug a water bottle straight in 30 seconds, you'll notice, give it about 20 minutes or so, and you're going to be peeing straight water because your kidneys can only handle so much at one time. So that's what we're going to be talking about. That's what we're going to be doing and manipulating. We're going to be moving things out and in of these tubules and in the bloodstream. As promised, I'm going to show you the actual anatomy of the nephron, what it should look like, and then talk about the 2 different types in just a moment. So we have our crazy glomerulus, we have our Bowman's capsule protecting it, right? And then, let's do that again. All right, and then we have our crazy PCT. I'm just going to draw some squiggles to give you an idea. PCT, right? And then we have the loop of Henle. All right, the loop of Henle actually wraps around this way, and what happens is the DCT actually goes right next to that opening of the Bowman's capsule. And then it can go either direction. It can go this way to find a collecting duct, or it can wrap back around and go this way. It doesn't matter. It just depends on the nephron. But what we're going to introduce in a little bit is we're going to have 2 types of cool cells in this area that interact with the glomerulus and the blood flow heading into the glomerulus and out of the glomerulus. So I wanted to show you what a nephron actually looks like. It's still same order. The filtrate actually, it goes glomerulus, Bowman's capsule, PCT, loop of Henle, and DCT. But the DCT is actually right next to that Bowman's capsule as well. It just wraps around, but it's still distal because it's not exactly directly connected. It's just right next to it. Okay, let's talk about the 2 types of nephrons, 2 classes. What I'm going to draw here is 2 vessels. So here's our kidney, and remember in our kidney we have renal pyramids, right? And we have vessels that arc around those renal pyramids, separating the cortex from the medulla, and we call those the arcuate. right? Arcuate artery, and we have an arcuate vein right next to it. Different types of nephrons. 85% of the nephrons in your body, what they're doing is they're just filtering things, and they're mainly found in the cortex. So the anatomy of that specific type of nephron looks like this. You have your glomerulus, and here's your capsule. And then you have your crazy PCT. You have the Loop of Henle, and the Loop of Henle just dips into that medulla. And then we have our DCT. And then it goes into the big collecting duct. So here's CD collecting duct. All right, so just in case we didn't quite understand this, remember, superficial to the arcuate artery and veins, this is the cortex. And then anything deeper to that, where those collecting ducts are going, heading towards those renal papillae, the openings, that's the renal medulla. So 85% of the nephrons in your kidneys look like this. They're called cortical nephrons, meaning they mainly stay in the cortex. The only thing is that tiny little piece of the Loop of Henle, that little bottom of the U, does dip into the medulla a little bit. The remaining, the 15% of the nephrons are called juxtamedullary nephrons, and they look like this. You have your Bowman's capsule, your glomerulus, your PCT, and their Loop of Henle goes way deep down into the medulla. And then same thing, it comes up, the DCT wraps right around next to that glomerulus, and then it will go this way to dump into the collecting duct. So big difference is the juxtamedullary go deep, deep down into the medulla. And what you're going to find out is, as you can read in the notes, this is what's going to help us concentrate our urine. It's really, really salty in those renal pyramids. The deeper and deeper you go down, the more salt concentration, the more sodium, the more chlorine, the more potassiums we have. So depending on our body's water needs, whether you want clear urine or very yellow urine or whatever, we're going to be able to manipulate the amount of water in these juxtamedullary nephrons, because wherever salt goes, water typically follows. So if we're sucking a lot of salt into the tubes, water is also going to be sucked into the tubes. If we're reabsorbing a lot of salt into the bloodstream, water is going to be being reabsorbed into the bloodstream. So what we're going to do is we're going to create this salt gradient, this concentration gradient of salt, and with the help of that, we're going to manipulate our water concentration to make sure we're hydrated. So only 15% of the nephrons in your kidneys actually manipulate the concentration of urine. The other 85%, we're really just focused on filtering, getting the bad stuff out and keeping the good stuff getting it reabsorbed back into the bloodstream. So those are the two types. So let's begin to put numbers to this to make this more of a reality for you. As all of this fluid is going through the millions of nephrons in your body, on a daily basis, 24-hour window, 180 liters of fluid is going through the nephrons. Now specifically, it's going through that glomerulus and that Bowman's capsule, and then remember, 70% of it just gets reabsorbed right back into the bloodstream, but 180 liters. And if you remember, we only have 4 to 5 liters of blood in our body, so multiple times, as you can see, the entire plasma 60 times a day, we are cleaning our blood. So somebody who is going through kidney failure and needs dialysis, they don't just say, oh, you need dialysis. You need dialysis because your body naturally is supposed to clean the blood multiple times per day, multiple times per hour, in fact. So out of the 180 liters of fluid that go through your kidneys in one day, only about 1.5 liters turns into urine. So if you do the math, you can see down here 1.5 out of 180 is somewhere between 1 and 2%. So only 1% or less than 1% actually gets turned into urine. And what that ends up being in your urine is any type of waste products or things we don't need. It doesn't always have to be a waste product. It can just be vitamin C, right? The example I mentioned earlier. If you have too much, your body will get rid of it. So what this is saying is 99% of the fluid that goes through your kidneys eventually gets reabsorbed back into the bloodstream and recirculates. Only 1% or less than 1% actually becomes urine. And you can, so as the kidneys are processing this, you can grow an appreciation to how much effort goes into making the urine, just constantly filtering. You could see other notes on this slide that 20 to 25% of oxygen is used by the kidneys alone. The other 75% has to, similar to the blood flow, right? The brain hogs up a lot as well. So the rest of the body has to fight for that extra 50%, or the remaining 50%. And as we mentioned earlier, what in the world is the filtrate? The ingredients of the filtrate is basically everything that can pass through those tiny little filtration slits, thanks to those podocytes and those pedicels and those leaky capillaries. It's basically your plasma. It's your plasma minus the big proteins that can't sneak through. So everything that's going to be small enough to sneak through those leaky capillaries and those filtration slits are going to go through to the Bowman's capsule and the PCT. Here's some nephron terminology. A few of these words we've actually already covered. There are three processes that occur throughout the nephron that are A, cleaning the blood, and B, making urine. And these three processes are, as you can see, number one is something called filtration or glomerular filtration. And all this is the movement of the filtrate, basically the plasma minus your big proteins that can't fit through those leaky capillaries. It's the filtrate moving in from the glomerulus to the Bowman's capsule, and then from the Bowman's capsule to the PCT. Now, how the filtration processes actually work, I'm going to show you on the next slide. But for right now, it's just movement of everything in the blood except your red, white blood cells, platelets, and big proteins. Tubular reabsorption, we've already covered. Reabsorption is just getting things back into the blood. So 70% of it happens right in the PCT, and the other 29% happens in the Loop of Henle and the DCT and the collecting duct. But all we're doing is we're taking that 99% of substances that, so if we have 180 liters of stuff going through the nephron, and we only make 1.5 liters of urine, you should know, doing the math, that 178.5 liters gets returned right back to the bloodstream. Right, simple math, or aka 99%. So the definition of reabsorption is taking those substances from everything in the tubes, the tubules, and putting them back in the blood, reabsorbing them into the bloodstream, because that's where they originally came from, right? And then tubular secretion is the complete opposite of reabsorption. We're taking stuff in the blood and we are dumping it in to the tubules. So this is the examples that I showed you with the Loop of Henle and the DCT, where we're dumping waste products such as urea and uric acid and ammonia, those kind of things. We're taking it from the blood and putting it into the tubes, so then it can eventually go to the collecting ducts and the minor major calyx and the ureter and then the bladder, and then get rid of it. So filtration, reabsorption, secretion, once again, these are the three processes that help you make your pee and help you filter your blood. Let's move on to the next slide and we'll talk about filtration. So filtration is a passive process, meaning that there is no ATP required. And what's driving this is the pressures of these fluids. Now recall what hydrostatic pressure is. Basically, this is the pressure from the fluid inside of your blood vessels. So if I was to draw our glomerulus, there we go, and then we have our Bowman's capsule surrounding it, PCT, like that. Remember, there are afferent arterioles, or afferent arteriole coming in and then an efferent arteriole going out. There is blood inside of these arterioles. So there is a pressure, right? And remember, the pressure in the arterioles drastically dips from our usual 120/80 in the bigger arteries, but there is still pressure. When you feel your pulses throughout your body, your radial pulse, your femoral pulse, your pulse in your foot, your dorsalis pedis, or whatever you call that pulse, the tibialis posterior area pulse as well, your popliteal pulse, all those pulses, there is a pressure. And the reason why you can feel those pulses is because the blood, as the heart pumps, the blood is actually moving and basically hitting those walls and stretching them. So there is a pressure inside with every single heartbeat, with every single pulse. There's fluid that presses against these walls. So hopefully you can appreciate the pressure. Now, as that pressure gets into these very, very, very small capillaries, what it does is it forces the fluid into the Bowman's capsule. Now, there are other pressures, that do act on this. There is a colloid osmotic pressure from the proteins that do move fluid back in towards the glomerulus. There's also hydrostatic pressure in the Bowman's capsule that moves it back here. But what happens is there's a nice little math equation that even though they're moving back and forth, there's a net pressure movement of about 10 millimeters of mercury that force the filtrate in to the Bowman's capsule, and then from the Bowman's capsule into the PCT. So let's go on to the next slide and I'll show you a better illustration. So here are all of the processes or pressures that are affecting the filtration rate. So if you look at the picture, don't worry about the words of the arrows right now, you'll see we have the glomerulus right in the middle of the picture. The Bowman's capsule is kind of surrounding it, and then we have our PCT. So as I mentioned, we have hydrostatic pressure just from the fluid inside of the blood vessel. And you can see that it's 55 millimeters of mercury. And remember, this is just a standard universal measurement of mercury, right? We measure length in inches and centimeters. We measure pressure in millimeters of mercury. And then you have other pressures acting in the opposite direction. You have hydrostatic pressure from the Bowman's capsule, and then you also have that osmotic pressure from the proteins that force it back towards the glomerulus. Notice the arrows where they're pointing. But what you get is this. You get a plus 55, I'll do that in green to stay consistent, plus 55 millimeters of mercury forcing fluid in to the Bowman's capsule. And then you get a 30 or a minus 30 from the osmotic pressure. So if you do the math real quick, that's going to be 55 minus 30 is a plus 25. And then you have an extra 10 hydrostatic pressure forcing fluid from the Bowman's capsule back into the hydrostatic pressure. And if you do the math, we get a positive 10 net pressure. So even though we have stuff moving back and forth, at the end of the day, what's going to happen is the force is stronger moving from the glomerulus into this Bowman's capsule. I'll do it in black. So fluid is moving in both directions, but the majority of it, or more than moving back in, or moving most of it out. And as it goes out, it's eventually going to go down towards this PCT, and then the loop of Henle, DCT, and you all know the rest by now. So that's filtration. Once again, passive processes happens naturally. You don't have to do anything about it. There's no ATP required. Now that we have the definitions down, we can actually apply this to the nephron. So once again, if you look at the glomerulus that I'll draw in, a bunch of weird capillaries everywhere inside the Bowman's capsule, this process driving the filtrate into the tubes, that is called filtration. Everywhere where you have the purple boxes that I'm starring or circling, purple, 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 those arrows are showing that this stuff is leaving the nephron and going into the bloodstream. We call that reabsorption. And then everything in those tan-like pictures, that is stuff leaving the bloodstream and being directed towards the nephron. That's what we call secretion. Now, secretion is different than excretion, right? Excretion is actually excreting, getting rid of the stuff in the body. Here, we are just moving stuff into the tubes, but we can still manipulate this. We can still change this. For example, with these hydrogen ions, like I said, if we are too alkaline in our blood, even though we're dumping it in this picture, we're dumping the hydrogen ions into the PCT, and here we're dumping it into the collecting duct. If our blood needs those hydrogen ions, we can reverse this. We can reabsorb the hydrogen ions to fix our pH. So secretion is just taking things from the blood into the tubes. It's not the same as excreting. Excreting is basically bladder to urethra outside your body. So we're not reabsorbing or secreting anything in the bladder. Next topic I want to introduce is something called the Juxtaglomerular Apparatus. It's also known as the Juxtaglomerular Complex. So in some of your textbooks it may say JGC instead of this JGA. And what the JGC does is help monitor filtration rate and therefore blood pressure. So how much filtrate is moving through this glomerulus can affect blood pressure and vice versa. So once again, the glomerulus is specialized for filtration, and it is special, it is different because, yes, we have an arteriole feeding into the capillary bed. That's not any special or different than anything else, but there's also an efferent arteriole draining the capillary bed, and that's what makes it unique. That's what makes it different. Because usually we go arteriole, capillary, venule. Here we have two arterioles. So on the next slide, we're going to zoom in or blow up this picture, and we're going to talk about how this actually works in regulating the filtrate and helping blood pressure. So same picture as previous slide, just blown up. And let's get our bearings right, our orientation right, so we can talk about this in more detail. What you're looking at is the afferent arteriole right here going in to the glomerulus. Now notice in this picture the glomerulus is covered by all of these weird podocytes, those cells that have all the tentacles or finger things. So these slits are very, very, very tiny, and that's done on purpose. Once again, take a look at this is a really great illustration. Take a look at the size of the red blood cells. The red blood cells in relation to these slits are huge. They're gigantic. There is no way that big red blood cell is going to fit in this tiny little crevice between these two little finger things. There's just no way. So the red blood cells are protected, and you can see how in this area right here that I'm circling in black, you can see how we exposed the podocytes or removed them so you can actually see the glomerulus. You can see these blood cells moving one at a time through these capillaries. And then we have the efferent arteriole leaving and going to the peritubular capillaries over here somewhere. Okay, so then surrounding that you can see Bowman's capsule. You can also see the PCT right here. And then from the PCT, remember we get our loop of Henle. So if I'm going to draw this the best I can, loop of Henle kind of loops like this. There's our big loop. And then we have the DCT and the collecting duct start to form. And that is what we're looking at right here. You're actually looking at the DCT. So the DCT and the PCT are kind of right next on top of that glomerulus. So two types of cells that I want to introduce to you. First, are cells actually in the DCT, these ones highlighted in green, they're called the Macula Densa. And these cells are really, really good at detecting salt levels in the nephron. So specifically sodium, sodium chloride is what we're detecting here, but it can detect other things. So remember, wherever sodium goes, water is typically going to follow. When we talked about hypertonic states and hypotonic states last semester, remember if a cell is in a hypertonic state, that means there's simply more concentration of something outside the cell. So if I was to draw a cell, there's our cell, and let's say we have 50 particles of salt on the outside, and we have 10 particles of salt on the inside of the cell. What's going to happen is one of two things. One, we have a concentration gradient, right? We have an imbalance, so that 50 is going to want to go to that 10. But that's not always the case. Sometimes it just doesn't move. So what we do is water tries to move and dilute the larger number. So in this situation, this is what we call a hypertonic environment, and water is going to leave the cell to try to mix in and dilute that outside environment, and by doing so, it'll concentrate the inside. So it'll balance it both ways. In a hypotonic state, it's just the opposite. If we had, let's say, 4 particles on the outside of the cell and we had 40 on the inside, it's just the flip-flop scenario. What's going to happen is water is going to move inside the cell. So in severe situations, the cell can shrink up or swell up like a balloon and pop, but for the most part, our bodies are constantly just making these minor adjustments with water movement. So wherever salt goes, water is typically going to follow. If you notice, the water is going from the low number of salt to the high number of salt. So what the macula densa does is it monitors salt levels. And if we have low salt levels, we're probably going to have low water levels. And if we have low water levels in that area, well, then we know that we're probably going to have some issues with blood volume or blood pressure, right? And vice versa. If we have high salt, we're going to have high water in that area as well. So salt's going to be the main theme. I'll show it to you on the next slide. The other type of cells that we're going to introduce are called the granular cells, or also known as the juxtaglomerular cells. And these are cells right on the smooth muscle. You can see them kind of in purple, right on the edge of the afferent arteriole, and there's also some in between the afferent and efferent arteriole. And these cells are the specific cells that actually release renin. And remember when we learned about the Renin-Angiotensin-Aldosterone System, the RAS, that's going to help us raise our blood pressure in situations where we have low blood pressure. This is what gets the whole ball rolling. That's what releases the renin, the first part of it. Now, they actually get feedback from either A, the macula densa, or B, the nervous system. You can see the renal nerve is right here talking to these smooth muscle cells. So sometimes the autonomic nervous system, fight or flight, can just take over and just say, hey, raise our blood pressure now. But for the most part, we're going to have these chemical receptors, these monitors, the macula densa, talking to the juxtaglomerular cell. Before we move on, if you look at the picture on the right, you can see a micrograph or a histology slide of what we're looking at here. And you can see the glomerulus is inside of this nice Bowman's capsule, this simple squamous Bowman's capsule right here. And then you can see pretty much everything else is going to be this simple cuboidal, where we have the PCT, the macula densa. Here's going to be the DCT. And then, and here, well, here's another DCT right here too. So that's what I wanted to point out is, if you notice, all these circles around that you see, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are millions of nephrons, right? So yes, we only can see one glomerulus. Here's a second glomerulus right here. But these things are all over the place, and they're all stacked right on top of each other, constantly filtering out your blood for you. So let's move on to the next slide and dive into the macula densa and the juxtaglomerular cells, now that you have a visual. Once again, here are the two types of cells. We have the macula densa and the granular cells, aka juxtaglomerular cells, or JG cells. You're mainly going to see them as in this format, juxtaglomerular. Once again, the macula densa has chemoreceptors. They detect salt levels inside of the tube. And in your notes here, it says ascending limb of the Loop of Henle, which basically runs right into the DCT. So I know I said DCT on the previous slide. These things border each other, so tomato, tomato. Same thing. Not the same thing, but they're right next to each other. And how the macula densa works is this. If we have low sodium chloride levels, remember, wherever sodium chloride goes, wherever salt goes, water's going to follow. So if we have low sodium chloride levels, we're going to have low water levels. And that kind of sends off an alarm to say, hey, if we have low water levels, we may have low filtration going on. And if we have low filtration going on, we may have low blood pressure. So then the macula densa sends a signal to these guys, to the juxtaglomerular cells, and say, hey, we need to do something to raise our blood pressure. So in both scenarios here, our problem is going to be that our blood pressure is too low, and our fix is to increase our blood pressure. So the macula densa does that by detecting low salt levels inside of the filtrator, inside of the tubules. So once again, these are chemical receptors. The juxtaglomerular cells do the same thing, they just detect it in a different way. So same thing, here's our problem, is decreased blood pressure. And remember, where these cells are at are along the walls of that afferent arteriole. So they actually are smooth muscle cells, and because they're on the walls of the smooth muscle, they are sensitive to stretch. So these are stretch receptors, also known as mechanoreceptors, and they detect changes in blood pressure due to stretch. So if we are stretching a lot, no big deal. That means we have a lot of fluid coming through this area, and we have a high or good or high or normal blood pressure, one of the two. If there isn't a lot of stretch, then that's going to indicate and say, hey, maybe something's up. If we're not stretching, that means we're not having a lot of fluid go through this area, and that means our blood pressure's maybe too low. And we don't want too low a blood pressure, right? If you think about from like a systemic standpoint, yeah, if you have low blood pressure, you may not be getting enough oxygen to your fingers and toes. You might be feeling a little dizzy, fainted, or lightheaded kind of symptoms. But from a kidney perspective, if you have low blood pressure, that means that 180 liters of fluid may not be getting processed through your kidneys. And once again, we need to clean this stuff 60 times a day. So with low blood pressure, you may not be cleaning it as efficiently, which can cause toxins and waste products to build up in your body. So we need that homeostatic range. We don't want our blood pressure too high because that can wreak havoc on the kidneys. And we don't want our blood pressure too low because then we can't filter things efficiently. So we need that kind of nice, happy middle ground. So what happens then is if we detect low stretch in the juxtaglomerular cells, we secrete the enzyme called renin. And then renin gets that whole train going with the angiotensinogen, angiotensin 1, angiotensin 2, the aldosterone, all that stuff we'll go over. But we should have already talked about it. So what I want you to know is the big difference between these two. They're working together. They're detecting low blood pressure, and they're trying to fix that low blood pressure. But how they detect them are two different ways. The Macula Densa detects it through salt levels, and the juxtaglomerular cells detect it through stretch levels, because there are two different types of receptors. One's a chemoreceptor detecting a chemical, and one's a mechanoreceptor or stretch receptor detecting stretch. So that is the JGA, the Juxtaglomerular Apparatus. Just a nice summary page trying to put it all together for you. Once again, the anatomy's a little off here. Remember that after we get to the Loop of Henle, the DCT, it wraps around this way. So here's the ascending limb, and then the DCT is this way, and then we go to the collecting duct. But that's really, really confusing for students and for me when you're first looking at it, if it's all jumbled and a big mess. To show it like a linear pathway like in this picture just helps you kind of bring all the ideas together with the filtration, reabsorption, secretion. So we had a review slide specifically talking about filtration. This is a review slide specifically talking about reabsorption and secretion, just showing you those definitions and going into a little more detail with secretion. So once again, reabsorption is we're reabsorbing things back into the blood. And remember, overall, we're absorbing pretty much, or reabsorbing 99% of the contents of this filtrate. Only 1.5 liters of urine are being produced per day on average. 70% of this, 99%, gets reabsorbed almost immediately in the PCT. And then the other 29% happens along the Loop of Henle, distal, convoluted tubule, and the collecting duct. So with secretion, once again, secretion is we are sending things from the blood to the tubes. So we're actually trying to get rid of this stuff eventually to excrete it, potentially. And you can see some of this is waste products. Some of it is just things that we can afford to get rid of, such as potassium. This potassium is stuff we can get rid of at times. Sometimes we actually need to hold on to potassium too, though. We're going to learn about aldosterone in just a little bit, and how aldosterone, one of the side effects of it is it holds on to sodium, so water can kind of follow the sodium. But it does, one of the side effects is it drains potassium, or it excretes potassium. But if you remember, that sodium-potassium pump brings in 3 sodiums and kicks out 2 potassiums. So we're still gaining more salty or salt potential or cations in this area. So water will follow that net charge or that net gain. Hydrogen ions, we've talked about before. This is going to be our main driver for pH. If you skip ahead to this bottom bullet with me, we control our pH in our blood by altering the hydrogen ion and the bicarbonate ion. Basically, the more hydrogen ions you have, the lower your pH is, the more acidic you are. And the more bicarbonate ions you have, the higher pH. Not technically, the bicarb is really just a buffer, but what the bicarb does is it grabs onto those floating H's and kind of neutralizes them. So you can make the statement indirectly, the more bicarb you have, the higher the pH, and therefore the more basic or more alkaline the pH is going to be. So if we are very acidic, we can urinate, pee out this stuff. The hydrogen ions, we can secrete the hydrogen ions and then pee it out. If we're very basic or alkaline, we can reabsorb these hydrogen ions. So it just depends on what the body needs, what the body wants. To keep that blood pH, remember that blood pH is really finicky, 7.35 to 7.45. Other reasons why we secrete, as you can see, nothing new here. We got to get rid of all the drugs and the junk that we put in our body. Breakdown of stuff, undesirable substances, urea and uric acid, just breakdown of protein and nucleic acid, just basically stuff that you eat you can't use 100% of your food. So some of it turns into fecal waste and some of it turns into urine waste. And then as I mentioned, the aldosterone, we'll get to that in just a little bit. So a nice little review slide just showing you the difference. Reabsorption, sucking it back into the blood. Secretion, taking it from the blood to the tubules. All right, y'all. Let's get a little weird and start talking about the regulation of urine concentration and volume. Recall that there are two types of nephrons in your kidneys. 85% of them are called cortical nephrons, which means they mainly just hang out in the cortex. That loop of Henle doesn't really dip into the medulla that much. The other 15% is what we called juxtamedullary nephrons, and their loop of Henles go way deep down in to the pyramids. And I said that was significant regarding saltiness levels and urine concentration. Here's where we're going to introduce those facts. All right, so let's draw a nephron, and we'll start with our glomerulus. We have our, getting kind of good at this, Bowman's capsule thing. There we go, our PCT, and then we have our loop of Henle. And the loop of Henle is going really, really far down into the medulla. And then we have our DCT where we see our Macula Densa cells. And then the DCT kind of wraps around to our collecting duct. All right, there's our nephron. Okay. So, inside of the nephron, at least right when it starts, we have this osmotic concentration of 300 milliosmoles. Now, what in the world am I talking about? Take a look at these definitions and you can get an appreciation of what I'm saying. Osmolality, all it is a number of particles. So here we're mainly talking about salt, but it can be referring to any type of particle in a kilogram of water. Now, in the body, we're only talking about so much fluid, right? So we actually, there are thousands of an osmol, so we call them milliosmoles. So in the body, just remember going back last semester, we talked about voltage, and we said that negative 70 millivolts was the normal resting potential. So if we had to make an action potential, we had to change that number. It's the same thing here. 120/80 blood pressure, that's your normal. Your normal milliosmoles, your osmolality, is 300 inside the nephron. Okay, so remember that there are capillaries all throughout this area as well. So I'm drawing what we call the vasa recta, meaning the very long loop capillary looking things, but we also have capillaries out here, and we have capillaries by the, there's capillaries everywhere, including the glomerulus, right? Red blood flow everywhere. So typically we have 300 milliosmol in the PCT. We also have 300 milliosmol in the blood. So they're actually equal. And then same thing, well, we'll talk about dehydration and stuff later. But please remember the orientation of the cortex and the medulla. I'm going to draw a big, huge purple line right here. And that's going to represent our base of the pyramid, or that arcuate artery, arcuate vein. So above this purple line, that is the cortex. Below the purple line is the medulla. So as we go deeper and deeper into the medulla, closer to those renal papillae, what happens is this osmolality gets more and more concentrated. So we get saltier and saltier. So I'll show 600 down here, 900 down here, and 1200 down here. And then same thing down here, that they're going to be a little different, maybe like 800,000, and then maybe like 500. Here we go. 300, that kind of thing. They're going to change based on our needs. So the bigger the number, the more saltier we are, and the blood happens to have the same thing. Now the numbers are a little different. There's always, generally speaking, there's a 200 amount difference. So if we were to have 300 inside the 2, we could have something like this, 500 and 300. And I know you probably can't read the handwriting. It doesn't really matter right now. All I'm just showing you is the deeper we go into the medulla, the saltier we're going to get. Okay, I'm going to show you accurate numbers and what's actually happening on the next few slides. As I've mentioned before, the kidneys are constantly making alterations and adjustments throughout our bodies, throughout our day. What we need to do if we're dehydrated, we need to make adjustments to hold on the fluid, to rehydrate ourselves. If we're overhydrated, we need to make adjustments to get rid of that extra fluid, right, to maintain homeostasis. How we accomplish this is through something called the counter-current mechanism. Now, what I'm going to do is same thing. I'm going to draw the Loop of Henle and just kind of try to bring it into a nice picture for you. So here is our PCT, and then we have the beginning stage of the Loop of Henle, and then the DCT. And that's all I'm going to draw right now. So we know the flow. We know that the filtrate flows from the PCT down that Loop of Henle, and then it kind of makes this turn around, this hairpin turn is what they call it, and then it goes up the ascending limb to the distal convoluted tubule. Okay, this is one part of the countercurrent mechanism. So notice what's happening here is, and in reality, these are microscopic pictures, so I'm going to draw it more of a hairpin turn. They're like this Loop of Henle. It's really, really long and skinny. And then, but inside of that, you have a really, really long and skinny capillary network, which I'm kind of messing up, but you kind of get the point. So what's happening is this: because filtrate is flowing down in one direction and then literally a millimeter away from it, the opposite direction, and that we can manipulate what's going on inside the Loop of Henle. We can move sodium and chloride back and forth. We can move water back and forth and change the concentration of the tubules. We can also manipulate this based on blood flow. The countercurrent mechanism also involves blood flow. So if we were to draw the blood flow, let's draw our afferent arteriole here. And then what happens is here's our efferent arteriole, and those capillaries can wrap around and go this way in the complete opposite direction of the filtrate movement. And then we can go to the venule and the cortical radiate veins and all the arcuate veins and all the veins that you learned eventually to the inferior vena cava. So there's an opposite flow of filtrate with the Loop of Henle. There's an opposite flow from filtrate to blood flow. So as we're moving things back and forth through reabsorption secretion, this countercurrent mechanism is what's going to set the stage for this balance of ion concentration. Now remember, our milliosmoles, our normal number is 300 milliosmoles here. And as we go deeper and deeper and deeper into the renal medulla, the pyramids, it gets saltier and saltier. So the blood's really salty, the tubule's really salty. But if we need to make it less salty based on our urine needs or based on our body's needs, we can make it less salty by moving things back and forth between the descending limb and the ascending limb of the Loop of Henle, and also just the blood flow itself. So here are the two types of countercurrent mechanisms. We have the countercurrent multiplier, which I'm going to show you. I'm not going to draw that because I'm just not that good of an artist, but I'm going to show you that that's the interaction between the loop of Henle. So we're going to have those two limbs, ascending, descending. They're going to be right next to each other, and the numbers are going to be a little off. One side is going to be always a little different than the other side, and that's going to allow us to manipulate, once again, these concentrations. And then the other one is the countercurrent exchanger, and that is the blood flow. So as blood flow is going one direction in the blood and the capillary, the filtrate is going the opposite direction in the loop of Henle. So when you put two of these together, we call it the countercurrent mechanisms, because we have blood involved and we also just have the loop of Henle involved. Take a look at this picture and you can see a more detailed representation of what's going on. Getting your bearings right, we're looking at the hairpin turn of the loop of Henle. So this would be the downward or the descending limb of the loop of Henle, and this would be the ascending limb of the loop of Henle, eventually going towards that DCT. So then the PCT would be kind of here, referring to this picture on the right. All right, so what I want to show you is, first, I want to show you the osmolality of the interstitial fluid, and therefore what's very similar to your blood flow. So if you look in the middle of the picture, you have 300. Remember, that's our kind of baseline normal. And then as we go deeper and deeper and deeper into those renal pyramids, we get more concentrated, more salty, and more salty. So now what I want to do is I want to take your attention to the descending limb of the loop of Henle right here. And it's the same thing. As you see, we have 300 getting saltier, 500, 700, salty, until we hit this kind of maximum of saltiness of 1200. Now, that may not seem like a big difference. 1200 minus 300 is 900, yes. But if you figure in terms of multiplication, that is 4 times as salty as your normal blood and normal interstitial fluid and normal tubule osmolality. So it's really, really salty when we get down to the very tip or the turn of the loop of Henle. Now, as we go back up towards that distal convoluted tubule, notice the numbers get smaller and smaller again until we actually get to 300 and even less than 300 in some cases. All right, so you can see the changes in numbers, right? You can appreciate that. So next thing I want to show you is the differences between the numbers from one side of this hairpin turn to the other. So I'm going to get this, let's try to do this in, we'll try to do it in black. If you notice, down here at the hairpin turn, they're equal. You have 1100 on the descending limb, you have 1100 on the ascending limb. But then what starts happening is these numbers change and they get a little off, and that's on purpose. So you have 900 on the descending limb and 700 osmolality on the ascending limb. Same thing here, take a look. 700 on the left, 500 on the right. 500 on the left, 300 on the right. And what you should be noticing is a pattern of difference here. The pattern is 200 milliosmoles. So the descending limb has a 200 milliosmol greater concentration than the ascending limb. And here's why this is happening. If you take a look at what happens with the ascending limb of the distal convoluted tubule, what is leaving the tubule going into that interstitial fluid and eventually possibly into the bloodstream? What's leaving it is salt, right? We have a sodium ion, we have a chlorine ion, put them together, you get sodium chloride. So by removing that salt in the ascending limb, we're making those numbers less salty. So you can see, even though it's 500 on the left, right here, it's now 300 on the right because we lost a lot of salt. That's one side of the equation. The next side of the equation is, look what we're doing in the descending limb on the left side of the picture. what are we losing in the descending limb that's going to affect our saltiness levels? We're losing water. If you lose water, you're going to increase the concentration of salt. So not only are we losing salt in the ascending limb, we're losing water in the descending limb, and that is why you see this difference of 200. So there's always going to be that difference of 200 in a normal loop of Henle, because, as I mentioned, depending on our body's extreme needs, if we're dehydrated, we need to manipulate this really quickly. We need to hold on to sodium. We need to reabsorb this sodium chloride back into the tube, and we also need to hold on to water back into the tube to hold on to all that fluid so we can get rehydrated. If we are, well, sorry, I misspoke, didn't I? We're going to bring the sodium chloride back in to the tube, and the water is going to have to stay back in the bloodstream, right? We want the water in the bloodstream if we're dehydrated. If we're overhydrated, that's where I was getting at. If we're overhydrated, then the water is going to return to the tubules, and we're going to pee that stuff out. So this difference of 200 between the descending limb and the ascending limb allows us flexibility to manipulate these numbers so we can concentrate our urine or dilute our urine on an everyday basis, right? If you drink a lot of fluids, you could be peeing every 20-30 minutes. In those 20-30 minutes, your nephrons are working like crazy trying to balance this stuff out. So let's move on to the next slide and talk a little bit more about this. So the two countercurrent mechanisms work together, the exchanger and the multiplier. Where we get the multiplier is the difference between those numbers. Also, just the difference between the cortex area where we have 300 milliosmoles, and as we go deeper and deeper, it doubles and eventually quadruples as well. So here you can actually see the numbers. In the cortex and in the interstitial fluid in the blood, our baseline normal is 300 milliosmoles. And then when we get to the very, very bottom of the loop of Henle, we have that big number 1200. Now, these limbs, the ascending, descending, they're not in direct contact with one another, but they are close enough to where the interstitial fluid and themselves can influence each other. So we are still getting stuff moving back and forth. And then, as I mentioned, the most important thing on this slide is the difference between the ascending and the descending limb, that gradient that we have. So if one side's 300, the other side's 500. If the descending limb's 700, the other side can be 500. Or, if one's 900, the other one's 700. So we can use this gradient in the collecting duct and make last-minute adjustments. Remember when we were talking about the filtration, reabsorption, secretion, even in the collecting duct, we can make these last-second adjustments with hydrogen ions and potassium and urea and even water to fix or mess with our concentration. So if we're overhydrated, we need to dump as much water as we can into that area, hold on to salts. If we're dehydrated, we need to hold on to that water. So the collecting duct is going to be making those last second adjustments thanks to this concentration gradient that we're purposefully designing in the loop of Henle. So that descending limb is moving sodium chloride back and forth. Sorry, the ascending limb is moving the sodium chloride back and forth. That descending limb is moving the water back and forth. So here, just a little review slide, nothing new, just showing you that there's always a difference of 200 milliosmoles between the descending limb and the ascending limb on the right. So the descending limb always tends to have 200 milliosmoles greater than the ascending limb, and it's because who's losing sodium chloride and who's losing water. And then you can see this difference, the multiplication. We can quadruple from 300 to 1200. So it gets really, really concentrated, really salty as we get to the bottom of that hairpin turn. And this is just a review slide showing you once again what's happening. Now remember, just to put it all together, is you have vasa recta, you have capillaries in this whole area. So as I'm saying that the nephron is manipulating and moving things back and forth and the collecting ducts making these last second adjustments, when sodium chloride leaves the tubes and goes to the interstitial fluid, the blood is catching it. The blood is what is catching this water that's leaving the tubes. So depending on hydration levels, we can move these things back and forth between the bloodstream, the capillaries, and the tubules, that interstitial fluid just being in the middle of the two. And then last but not least, we have just a review showing you the countercurrent exchanger is talking about the blood flow, the capillaries, called the vasa recta. And the vasa recta is highly permeable to pretty much everything, right? They're capillaries, so they exchange is where they're simple squamous epithelium. They need to have stuff moving in and out. So both water and our salts are going to be moving in and out. And as I mentioned, they are opposite of one another, right? So the blood flow is going one direction, and the tubule flow, the filtrate flow in the tubules, is going the opposite direction with that loop of Henle. So that concentration gradient allows us to make those last second adjustments. So when you pee, when you go to the bathroom and your urine is really, really clear, or it's really, really dark yellow, or it's just a mixture between the two, you can thank your nephrons and your osmotic gradients for making those tiny little minute adjustments to make sure you're not overhydrated or dehydrated, because both are bad. All right, so hard part's done. All we have to do for the rest of the chapter is talk about GFR on this slide. We'll talk about how hormones affect GFR and urine concentration. Then we'll talk a little bit about urine. We'll talk about the ureters, bladder, urethra, and wrap everything up. So GFR, as you can see, stands for glomerular filtration rate. And this is kind of the gold standard of measuring how your kidneys are functioning. Are your kidneys working properly? Is usually dictated around the GFR measurement. And you can see, and you need to know this normal, is 120 to 125 milliliters per minute of filtrate being formed. So basically, blood from the afferent arteriole is rushing into those, the glomeruli, the capillaries, and then we're making about 120 to 125 milliliters per minute of this in our kidneys. So, how we actually measure this, there's two really cool ways. One is creatinine. Creatinine is a waste product that's made from like muscle tissue, and it's just a normal byproduct, waste product that circulates in your bloodstream. You can take measures of creatinine. You can just take a blood sample, and if you have high amounts of creatinine, that means that your kidneys aren't filtering it properly, and therefore it's probably not filtering other things properly. A more accurate way of measuring this, it's really cool. They give you this substance called inulin, which is basically just a carb found in like plants. And inulin is something that doesn't get reabsorbed or secreted well. So basically you put it in your body and you just pee it out almost instantly. Kind of like that stuff in asparagus, right? You eat asparagus and then within 20 minutes your urine smells like asparagus. Same thing. So they measure, or they can measure, how much of this substance is in your urine. So you do actually, and you can also do a blood draw too and see how much is in the blood. But if you have below 120 milliliters per minute, then that could mean that kidneys aren't working as well as they should. Now, before we start talking about pathology, let's do some math together and bring this all together. Really cool. So 125 milliliters per minute. Milliliters per minute. So remember when we talked about cardiac output, we talked about this as well, milliliters per minute. So how many minutes are in an hour? So hopefully you said 60, right? So if we were to do this, if we were to do 125 times 60, what you would get, carry the 3, 15, carry the 1, you would get 750, and then add that 0, you would get 7,500 milliliters. So that would be 7,500 milliliters per hour, right? All right, and then how many hours are in a day? I'll draw it down here so we have a little more room. 7,500 milliliters times 24 hours in a day. And what that gives you is, well, just take my word for it. What that gives you is 180,000 milliliters. Now, if we were to convert milliliters to liters, all we would do is move the decimal over 3 places to the left. So 180,000 milliliters is the exact same thing as saying 180 liters. Now remember, how much filtrate actually goes through the body in one day, goes through those kidneys? Or how much blood does your kidneys filter or take on throughout the day? In a 24-hour period, it's 180 liters. So this GFR is just measuring, are we actually filtering 180 liters of blood? What it's measuring is how much per minute. So pretty cool, right? Remember, 180 liters, 178.5 of that, or 179, is getting reabsorbed back into the blood. Only 1 to 1.5 liters are actually becoming urine. So anything, that second bullet point, anything below half of this range, so if you're functioning at half kidney function for a period of 3 months or longer, then you are officially in chronic renal disease. Now there's a lot of stages. There's stage 1, stage 2, 3, 4. I think there's a 5th stage. Some of you who work in dialysis clinics, you might be able to correct me if I'm wrong. I know it goes to 4. And I think end-stage renal failure could be considered 5. I'll have to look that up. But anyway, the leading causes of this, leading causes of your kidneys malfunctioning, there are many, many causes, but the 2 leading ones that you need to know is diabetes. And when I say diabetes, it's uncontrolled diabetes, right? You can live with diabetes and manage it properly and you'll be okay. But long-term diabetes for years and years and years and years, and you're not doing a great job controlling your blood glucose and insulin levels, and hypertension. Long-term uncontrolled hypertension. Remember when we were talking about filtration, how those pressures is what's moving the fluid from the glomerulus to the Bowman's capsule. If we have high blood pressure, we're going to be overworking the kidneys, and overworking the kidneys for months and months and years can lead to the kidneys not working properly and eventually breaking down. Now, once we get to end-stage renal failure is below 15 milliliters per minute. So just take a look. I mean, normal is 120, and end-stage renal failure is 15. Basically, this is it's like 10 to 15% of your normal kidney function. So when your kidneys when you're in end-stage renal failure, 90% of your kidneys are basically not working. They're shut down, and you're not peeing pretty much at all. And then extreme measures must be taken. Here is where you have to have the dialysis multiple times per week. Otherwise, you will die. And hopefully a kidney transplant is in the near future. So that is GFR. So how do we regulate the GFR? How do we make sure that our glomerular filtration rate is between 120 to 125 milliliters per minute? Well, it depends on your blood pressure. The blood pressure is what's driving the speed of the blood and the amount of blood going into that afferent arteriole that goes into the glomerulus. If you have the right number going into the glomerulus with the right pressure, you'll get that normal range. Now, it does vary, right? I mean, of course, not everybody has 120/80 blood pressure. I would argue that most people don't have 120/80 blood pressure. But as long as it's within a certain range, the glomeruli, because you have so many of them, you have millions of them, they can play catch up or slow down as they need to. So how this works is, if we have low blood pressure, that's a problem. So we need to raise blood pressure. And there are many different ways we do this, but with the kidneys, one way we accomplish this, so in green is our fix, and then red is our problem. One way we accomplish this in the kidneys is the RAS, or the RAM, whatever way you want to say it, the Renin-Angiotensin-Aldosterone System or mechanism. Main mechanism for increasing blood pressure in the kidneys, and the three ways that this gets started or gets initiated is we've already talked about. So the whole thing starts with renin. That's why it's called the renin blah 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 blah, right? It all has to start with renin, which is just an enzyme released from the kidneys from those juxtaglomerular cells. And three ways this gets activated. Number one is just through the sympathetic nervous system, fight or flight. What's going to happen is hypothalamus says, hey, we need to go into more of a fight or flight mode. We need to squeeze down on the afferent arteriole. So we have nerve fibers that actually go to the smooth muscle. Remember, smooth muscle can vasoconstrict or vasodilate based on our autonomic nervous system. So in this case, it's going to squeeze down to increase blood pressure. And then we talked about the two types of cells involved. We talked about the chemo receptors inside of the macula densa that detect the chemo or the chemical sodium chloride. And then I don't know why I'm drawing numbers. You can see the numbers right here, but to stay consistent. And then we have the stretch receptors or the mechanoreceptors in those juxtaglomerular cells or the granular cells. And number 2 and number 3, the macula densa and the juxtaglomerular cells secrete renin and get the RAS system moving. And then also direct stimulation of the sympathetics. Now, let's flip-flop it just for a second. What if high blood pressure is our problem? And then what we need to do to fix it is we need to lower blood pressure. Well, then what we have to do is we have to do the complete opposite of all this on this page. What we're going to have to do is we are going to have to stop sympathetic activity and initiate parasympathetic activity to slow down everything. What we're going to do is hopefully the macula densa cells will not be stimulated because we'll have high concentrations of sodium chloride. If we have high blood pressure, there's going to be a lot of stretching in the granular cells. So basically what happens is you cut off renin. Renin is not made, and if you don't make renin, you don't make angiotensin. And if you don't make angiotensin, you don't make aldosterone, and then this whole thing doesn't work, so it's not affecting, it's not raising your blood pressure. So hopefully by inhibiting it, you'll lower the blood pressure. And once again, the body is constantly making these adjustments. We're constantly releasing renin, stop releasing renin, release more, release less. We're constantly making these adjustments to maintain homeostasis and that sweet spot of 120 to 125 milliliters per minute of your GFR. So let's move on to the next slide and do a little review of the RAS system that you should already be familiar with. Alright, so it all starts in the kidney. It all starts with renin. So get your orientation right with this star that I just drew. This is our bloodstream. And then as we kind of go along this assembly line, we are going to introduce things into the bloodstream. So here's number 1. Here's what happens first. The macula densa senses low sodium chloride levels inside of the tubules. And that's what tells the juxtaglomerular cells to secrete renin. Also, the juxtaglomerular cells can sense not a lot of stretching going on, so that will secrete renin as well. So we release the enzyme renin into the bloodstream. Okay. The liver constantly releases another enzyme called angiotensinogen into the blood, and this thing's just floating around all over the place. Angiotensinogen, no big deal. And both of them are absolutely useless. Renin is useless, doesn't do anything. Angiotensinogen, totally useless, doesn't do anything. It's not until you combine the two where we get this kind of I guess you can say super molecule, or this just combination molecule called angiotensin 1, where we can kind of start getting the ball rolling. And I say kinda because guess what? Angiotensin 1 is also kind of useless. It doesn't do anything. But as angiotensin 1 is circulating through the bloodstream, it's eventually going to get to the lungs. And inside the lungs, you have this really cool other enzyme called ACE, which stands for angiotensin converting enzyme. And then what happens is, it, as it says in the name, converting enzyme, it converts angiotensin 1 to angiotensin 2. And that, my friends, angiotensin 2 is where the magic happens. So everything else prior to angiotensin 2 is useless. It doesn't do anything. But if you remove one of these from the equation, everything falls apart. It's kind of like a domino chain. If you remove one domino, then the rest of them won't fall. So you need renin and angiotensinogen to make angiotensin 1 to combine with ACE to make angiotensin 2. If you remove one ingredient, the cake isn't going to taste good. How's that analogy? All right. So what does angiotensin 2 do? It does a lot. We'll talk about a couple things on this slide, not everything. Number one, angiotensin 2 causes widespread vasoconstriction. So remember, the problem, why we're initiating this RAS system, or this Renin-Angiotensin-Aldosterone mechanism, is the problem is blood pressure is too low. So therefore, we're not getting enough blood through the glomerulus and the Bowman's capsule at a decent enough rate, and therefore our GFR is low. So we need to fix that. So one thing we do to fix it is we just squeeze on all of the blood vessels in our body. By squeezing on the blood vessels, just like if you're watering your garden, if you squeeze on the hose or put your finger over the opening, you're going to increase pressure. That's what we're doing, essentially. Number two is right here. ADH, antidiuretic hormone, causes, as you can read, aquaporins in the collecting. Basically, what ADH does, antidiuretic, is it makes you pee. So it holds water in by moving it, check it out, in from the collecting duct. So aquaporins to move to the collecting duct to reabsorb the water. So remember, those last second, those last minute adjustments that can be used to make concentrated or dilute urine with that whole countercurrent mechanism we just talked about, hormones can affect it. And ADH causes us to develop proteins on that collecting duct and suck that water back into the bloodstream. So by sucking water back into the bloodstream, you're affecting blood volume. If you increase blood volume, what are you doing to the pressure? You're increasing blood pressure. So that's what we're doing with ADH. Number three is we secrete a hormone called aldosterone. Aldosterone comes from that adrenal cortex. And the adrenal cortex, take a look at what it does, is it tells the body to hold on to sodium. Now there's a side effect to that. It does get rid of potassium, as I mentioned, but we're going to hold on to more sodium than we're going to get rid of potassium. And wherever sodium goes, wherever salt goes, generally water is going to follow. So by holding on to sodium, we're going to hold on to more water. And same thing, if we hold on to more water, we're going to increase blood volume, increase blood pressure. A fourth thing that angiotensin 2 does, I'll put it in the upper left-hand corner area. Number four is it increases your cardiac output. So it increases heart rate and stroke volume to an extent. And by doing that, you're going to increase blood pressure. You increase blood pressure, that's what we're fixing. And the last thing it does, or 5 out of many, is it increases your thirst levels. It talks to the hypothalamus to make ADH, but it also tells the hypothalamus, yo, I'm thirsty. So if you're thirsty, your brain is going to tell you to drink water or drink something, right? Not water, but anything. If you drink anything, it's going to increase volume in your blood, especially water. If you increase blood volume, it increases blood pressure. So the problem was our blood pressure was too low, and therefore our GFR was being affected. And by the help of all these enzyme reactions, eventually forming angiotensin 2, we're doing all these things to increase blood pressure. The kidneys are making this whole wave of systemic actions affecting the adrenal gland, affecting the brain, affecting blood vessels all over the place. Thanks to, it all starts with renin, and then eventually leads to angiotensin 2. So make sure you know how that system works, and make sure you know the effects of RAS, how we fix blood pressure. Now that we've covered hormones and we've covered osmolality with that countercurrent mechanism, let's bring it all together full circle. So Remember, the reason why we have that concentration gradient, the difference between the ascending limb and the descending limb of 200 milliosmoles, is so we can make those last second adjustments and manipulations, even in the collecting duct, last second. So if everything was the same, if everything was 500 milliosmol or 300 milliosmol, we wouldn't have any movement, right? If everything's the same, if it's isotonic, nothing would ever move and change, and your urine would always be the same. But we can't have that, right? Unless you eat the same thing and drink the same thing 24/7, we're constantly having to change our internal and external environments in our cells. So we need that gradient. And as you can see, without that gradient, you wouldn't be able to change the urine concentration. So in cases of overhydration, we have too much fluid in the body. We need to get rid of that fluid without getting rid of the solutes, right? So if you have too much water, let's get rid of the water and not the salts, because the salts are still important, right? Sodium and potassium help your neurons in your brain work. They help your muscle cells contract. Very important. So we don't want to lose too much of that just because we drank too much water. So in cases where our ADH decreases, so this is kind of a double negative, anti-diuretic goes down. So anti, which means we're going to be peeing a lot. In cases where you're peeing a lot due to low antidiuretic hormone, you're going to have very dilute urine. Remember, our normal is 300 milliosmol. So it can actually go down by a factor of 3, or a third of normal, if we have low ADH. And this is what happens when we drink alcohol, right? When we break the seal, and even though you're drinking beer, liquor, wine, or whatever you're drinking, you're pretty much just peeing water out the rest of the night because alcohol shuts off this hormone for the most part. And then another example is aldosterone. If aldosterone is present, additional ions can be removed, right? We can hold on to that sodium a little bit more, but we can flush out a lot of potassium too. But the balance we're holding on more sodium than flushing out potassium, so we can even get more diluted. So this is a synergistic effect. Remember the RAS system, what we just covered on the previous slide, what it leads to is angiotensin II. And angiotensin II causes ADH to be manipulated, and it also causes aldosterone secretion. So this is a synergistic effect where, depending on our body's needs, we can dilute urine with ADH, and we can make it even more dilute with aldosterone. So let's move on to the next slide and talk about the opposite. What happens if we're really dehydrated? If we're really dehydrated, then our urine is going to be very, very concentrated because we want to hold on to the water, right? So really the only thing we're peeing out is, it has to be a little water, it's still liquid, but we're really peeing out a lot of those solutes, a lot of those salts. So it's going to be really, really, really salty. And as you can see, 99% of the water is going to be reabsorbed. We're going to try to hold on to every single ounce of water in our body as possible to limit the effects of becoming more dehydrated. When discussing clinical evaluation of urine, one of the easiest ways to look at urine is peeing in a cup and running it through a urinalysis. Now, there are machines that work and do a lot of the analysis for you, but you can also do this cool manual urinalysis. You can pee in a cup and take a strip, or urinalysis strip, and put it in the urine, and then take it out and you take a look and compare it to what's on the label of the cup right there, and depending on the colors, it shows you if you're normal or abnormal in certain categories. So let's move on to the next slide, and we can talk about some of the things you'll see on a urinalysis. One more note is you can also test for blood as well. Blood is a good way of determining renal function. We'll talk about that as well. So when looking at a urinalysis, there are a lot of things that you'll find. We'll talk about some of these characteristics on the left. We'll talk about color and odor and pH in just a little bit. But I do want to point out some things that we should definitely not see in the urine. For example, your white blood cells, right? We shouldn't see anything with leukocytes or white blood cell, anything in there, 0 to 2 or none. If you do have white blood cells in the urine, we are definitely looking at some type of infection going on. You should not see a lot of protein in the urine, right? We want a lot of those protein and amino acids to be reabsorbed into the bloodstream, specifically in the proximal convoluted tubule. And then there's some cool other things that we should not really see. You should not see ketones in the urine. So that's one of the big things with the ketone diet. They say, check your urine. You can see ketones in the urine. You shouldn't have ketones in the urine. Ketones, once again, is a starvation mechanism. It's a thing to prevent you from starving. So you break that down and use it for energy. If you're peeing that stuff out, there could be something wrong. Also, we definitely don't want blood in the urine ever, right? We don't want any type of bleed. And glucose. We don't want sugar in our urine either, right? We want to reabsorb that sugar because we use that sugar, combine it with oxygen to make ATP in almost every single cell in our body. So we want to hold on to that kind of stuff. So just a few notes on urinalysis. Here are a few characteristics of urine. Generally speaking, the chemical composition is 95% water, 5% solutes. And I say that that's general because if we're overhydrated, it's going to consist of more water, right? Closer to 97, 98, 99. If we're dehydrated, it's going to consist of less water, right? And more solute. So it just depends. A few of the waste products that you should find in your urine. So if this shows up on a urinalysis or just in any type of lab, you should see this in your urine. This is normal. This is waste product that's found in the body that we do like to excrete. So you see urea. Urea is something that we break down from proteins, so your amino acid breakdown. And the more protein you eat, the more urea you should have in your urine. We have uric acid, which is from nucleic acid breakdown. So pretty much if you ate anything that ever lived or used to live, such as a fruit, a vegetable, or an animal product, even nuts and seeds, they have nucleic acids, right? They have DNA. Anything minus like a Pop-Tart maybe, it has some type of nucleic acid. So you will find uric acid in the urine as well. That is normal. And then creatinine. And creatinine is a normal metabolite of that creatine phosphate pathway. Basically what that means is muscle breakdown. As muscles just get worn down, this is a natural byproduct. Also, not even wearing down, as we use energy in the muscles. Creatinine is a normal waste product from using creatine phosphate to make ATP to give us energy in the muscle. So creatinine is one way we can test for GFR. We can take a blood sample, not a urine sample, but we can actually take a blood sample and see how much creatinine is in the blood. If we have a lot of creatinine in the blood, that means that our kidneys aren't processing it, they're not filtering it, and we're not peeing it out. So that can indicate some type of GFR issue. There's also another substance called inulin that does the same thing. We actually, you can take both a urine and a blood level of that to see if the kidneys are functioning. So as you can see on the bottom, anything that's abnormal, that's high, we should kind of be alarmed. It could indicate some pathology, proteins, white blood cells, even bile in the urine. You saw on the previous slide the urobilinogen, those kind of things. That's not, you don't want big traces of that stuff in your urine. Other things to consider with urine is the color and the transparency of your urine. First and foremost, let's talk about transparency. Your urine should be clear. It should be see-through. So if you were to pee in a cup, you should be able to look in that cup and see the other side of the cup. Or if you urinate in the toilet bowl, you should be able to see the bottom of the toilet bowl. It should not be cloudy or opaque by any means. If it is, as you can see, we could be talking about some type of infection or disease process. Now, let's talk about the color real quick. The color of urine typically is, the reason why general urine, it can be a yellowish color, is the breakdown of urochrome, or the releasing of urochrome, which is from hemoglobin breakdown. So your red blood cells, that protein inside your red blood cells has to get broken down. And that's what gives us the normal yellow tint of our urine. It's also hemoglobin breakdown, as we learned earlier, is also the reason why the stool is kind of a brown pigment. So A lot of folks tell people, and especially kids, and I was told this as a kid, that if your urine's not this color, if it's not like water, you're not drinking enough water, you're dehydrated. Okay, that may be true in some cases, but what if I take a multivitamin and I only need 10% of that multivitamin? The other 90% is going to get flushed out. So what that means is you should have a little color to urine if you're flushing things out. That means your kidneys are working. So I wouldn't strive for clear urine all the time. If your urine's yellow, that means your body is getting rid of waste products. So it's getting rid of water and other things. If your urine's just straight water all the time, you're just peeing out water. So, I mean, drinking all that water, is it really doing you any good if you're just peeing it out all the time? So take that with a grain of salt. One thing that I'm careful with in the summer is as I'm like working out or doing yard work, you want to make sure that your urine doesn't get too dark because that could be due to dehydration because you're sweating all the time, right? But if it's winter and you're just, doing your normal thing and your urine's a little bit of yellow, that doesn't mean you're dehydrated. You're okay. So things that can cause abnormal urine or abnormal color is a whole lot of things. Certain foods. Y'all, the first time I ate beets or drank a lot of beet juice, I thought I was dying. I thought I had cancer. My urine was red, and literally I thought I was in big trouble. Google helped me out a little bit there when I was younger. But a red orangish tint can be bad. That could indicate blood. That could also indicate liver issues. So you want to make sure that if you haven't eaten beets and your urine's red, that could be an issue. Biopigments, if there's some kind of obstruction, that can cause issues. I mentioned blood. Drugs can do a lot of crazy things to your urine. Just off the top of my head, some antibiotics. My grandmother was on the antibiotic for a long time. Her urine was always bright orange, and it was due to the antibiotic that she was on. Propofol, the crazy drug that knocks you out like instantly. It's a general anesthetic. It's a sleepy drug. Makes you go night night real quick. That can change your urine to like a blue greenish color, short term. And my wife took some anti-malarial drugs when she got back from Africa after a few trips, and that can change the urine like really, really dark brown, kind of like Pepsi, Coca-Cola brown. So those can be side effects of certain drugs, and I'm sure some of y'all know other medications and drugs that can mess with your urine a little bit. So take that whole clear thing with a grain of salt. If you're on a medication or a vitamin supplement, don't stress out that your urine's not water clear. That's probably a good thing because you're flushing the stuff you don't need. On this slide, we're talking about odor and pH. So with odor, your urine does have a little scent to it. I mean, if you stick your nose in a cup of urine, it will smell a little bit unless it's just pure water. And as that urine sits for a long time, it will develop a pretty strong ammonia smell because of bacteria that break down that urea. It gives off that very strong alkaline ammonia smell. And this has unfortunately happened to me a few times. You go to the bathroom before you go on vacation, and trying to save water, trying to be a good citizen of the earth. And if it's yellow, let it mellow, right? And you forget to flush the toilet before you go away for 4 or 5 days, and then when you come back, your bathroom and half the house just reeks, right? My bad. But that's because of that urine, that stale urine just sitting there for a long time. A lot of bacteria cause that ammonia smell to occur. So flush the toilet before you go on a trip. Drugs can also affect the smell. Veggies can alter the smell as well. Asparagus being the number one example, right? Disease can alter the smell as well. Diabetes being a big one. If somebody's diabetes is not under great control, you can get this, even in your breath, you can get this kind of fruity acetone breath, but you can also get a fruity smell to the urine. And it's not like a good fruity smell, it's like a fermented fruity smell, kind of like a old wine smell. That doesn't, I don't know, some people like wine. but that can affect the smell of the urine as well. pH of your urine, it's a very wide range, so it really just depends on your diet. As you can see, please make note of this range. Your urine can be 4.5 to 8. Now remember that 7.000 is straight neutral. That's just pure water with nothing in it. So 4.5 is pretty acidic. I mean, that's 100 times more acidic than just normal water, 150 times. Or wait, would that be 500 times, excuse me, 500 times more acidic than water. And then it can also be alkaline, so it can be 10 times more basic or alkaline than water. But generally speaking, average Joe Schmo who eats a little protein, little veggies, little this, little that, normal people's pH is a pH of 6. So a little acidity, but not a lot. Not a lot. And the more protein you eat, whole wheat can affect it as well, but the protein is the big one. The more protein you eat, the closer you're going to get to this 4.5. And you're also going to get more of that urea breakdown, that more smelly urine. The more vegetarian, vegan route you go, the more basic alkaline your diet, you can get it closer to that 8. Other things that can cause alkaline pH in your urine, prolonged vomiting, which is not always really good, and also UTIs can throw that thing off as well. So it's not always totally based on diet, but for the most part, if you're somewhat healthy, diet really affects the pH, and you can just change this day to day based on what you eat. All right, all we have to do now is just cover the rest of the urinary anatomy and a little bit of physiology. So we have the ureters, and then we're going to go down to the bladder, and then we're going to go down to the urethra, and then control of all that, and we are done. So the ureters, as you can read, very slender tubes that are connecting the kidneys to the bladder. They are also retroperitoneal, so they are behind all of that digestive viscera, and they actually enter the bladder through the posterior wall. I'll show you a picture in just a little bit. All right, let's discuss the histology of the ureter, and I got good news for you. The histology of the ureter is pretty much the exact same thing as the histology of the bladder, so we're kind of knocking out 2 birds with 1 stone here. From the inside out, so if we have a tube like this, on the very inner lining of the tube where the urine is actually touching, that is called the mucosa. So that's the deepest part, just like the digestive system, right? We had the mucosa epithelium, same thing here. Big difference though. Big, very important change or difference than any other tissue in the body is this is where we find transitional epithelium. No simple squamous, no simple cuboidal, columnar, any of that mess. It's a hybrid. It's a multifaceted epithelium. We're going to have a combination of all 3 of those shapes. And remember back to last semester, this only occurs in the urinary system. And the reason why is because with urine passing through these tubes, it stretches this epithelium, especially in the bladder, but also the ureters. So and we all know this, if you drink a lot, you go to the bathroom a lot, right? So as your bladder fills up, it compresses these cells and it can squish them and change their shape. As you go to the bathroom and relieve yourself, those cells stretch and expand and change shape. So this is the only place in the body where this is actually found, transitional epithelium. It's in the urinary system, mainly your ureters, bladder. The second layer is the muscle layer. So let's just draw in blue lines. Right on the outside of the mucosa is smooth muscle. And smooth muscle contract in response to stretch. So basically we're doing peristalsis is what we're doing. And as urine is passing through the tubes, the smooth muscle cells contract and squeeze it through. So even as you're sitting right now, your ureters are gently squeezing urine down into your bladder. And then after 20, 30, 60 minutes or whatever, you're going to have to go to the bathroom. So just like we had peristalsis of smooth muscle in the esophagus and in the intestines, we have the same thing here in the ureter. And then on the very outside of the muscle, we have this third layer, the most superficial layer, and it's called the adventitia. And all it is fibrous connective tissue. It's just protection. So as the ureters have to expand and as those muscles contract, we want to just make sure that stuff doesn't get damaged. It's protected. We're not having infection get outside the ureter if we have a UTI or something like that. So it's just a sheet of protection. So here you can take a look at the picture. Once again, from deep to superficial, we have mucosa, muscularis, and adventitia. The mucosa is what lines the lumen, and you can see the lumen right in the middle of the page. That's where the urine is actually going to flow. So in black, that is going to be the mucosa. All of this crazy mess in purple, that's the muscle. And you can see that it's a pretty decent amount of smooth muscle around the ureter that contracts it. And then on the outside, once again in black, you'll see the adventitia. And it's just a big protective network. Gives it that nice circular shape and makes sure that nothing damages or gets out of the ureter. You don't want urine leaking out of the ureter, right? Good news for the bladder. It's the same three layers. So we have the mucosa, same type of epithelial tissue. It's transitional. We have a little bit more muscle in the bladder. So we do have 3 layers of smooth muscle. Still smooth muscle though. A very thick muscle called the detrusor muscle. And what that actually translates to is push down. So it's going to be pushing the urine down towards that sphincter that's going to open up into the urethra. So that's unique to the bladder. And then we have the adventitia, once again, just for protection. As you notice on the very, very top surface, though, the bladder actually is covered by the peritoneum. But for the rest of it, the anterior, posterior, sides, all that stuff, it's going to be adventitia protecting it. As I mentioned earlier, the urinary bladder is just a sac. It's just a storage bag that holds your urine temporarily until we're ready to get rid of it. And we're going to talk about the brain control, right? There's got to be a good time to get rid of it. We just can't empty our bladder whenever we want. We have to time it to where we're, in the restroom. So we'll talk about nerve control in just a little bit. Where it's located is on the pelvic floor, just behind the pubic symphysis, and male and female bladders are pretty much identical. It's just the stuff around them is different. So with males, you have the prostate gland just below the bladder, and the prostate gland allows both urine and seminal fluids to enter, or prostatic fluid and seminal fluid to enter that same tube, the urethra. We'll talk about that when we get to the reproductive chapter. And then females, it lies just anterior to the vaginal canal, cervix, and uterus. Now, the bladder itself, I'm going to show you a picture in 2 slides. The bladder has a total of 3 openings on the posterior, kind of inferior side, or at least mainly inferior side. 2 of them are for the ureters, and 1 is for the urethra. And what it does, these 3 points make a triangular looking shape, and that's called a trigon. And I'm going to show you that on the next couple slides. So here you can identify the difference between female and male urinary systems. Just to kind of give you a little orientation, this structure right here is the female uterus. And then here would be the cervix and the vaginal canal that I'm highlighting in red. So the bladder does lie anterior to that. And we'll talk about the different openings of the female anatomy in the reproductive chapter. And then if you look at the male bladder, you can see it has an extra gland right below the bladder. That would be your prostate gland. And once again, we'll talk about all the cool functions of the prostate when we get to the reproductive chapter. So this is a picture of the bladder. First thing I want to point out is the small picture on the bottom right. Once again, what you see lining that mucosa is transitional epithelium. If you really, really zoom in on these cells right here, it's just a big hybrid mixture of flat pancake cells, cube-like cells, and big rectangle column cells. It's a mixture of all 3 shapes that we see in epithelium, only specific to the bladder and the ureter-urethra area, the urinary system. Okay, so take a look at the picture on the left now, and we can introduce some things. you see that the bladder is this big thing right here. All right, the big pouch. Leading into the bladder are the ureters, and the ureters go behind the bladder, and they open right here at these tiny little openings. And then once you get to the very inferior aspect of the bladder, you get this second opening, or this third opening, called the urethra. Now we have two sphincters lining the urethra, but the urethra is where it starts to open. And once again, as I mentioned, what you get is you get this kind of triangular looking shape right here, and that's called the trigon. And it's just the two openings for the ureters, and then the one opening for the urethra. Other things that you can notice that we've talked about, you can see the detrusor muscle, the smooth muscle here, and green. And then lying on top of that bladder, once again, is peritoneum. Everything else around it is going to be that fibrous adventitia, but on top of it actually is peritoneal lining. And then, very similar to the anal sphincters, the anal openings, we had an internal and an external, and one was involuntary, one was voluntary. It's going to be the exact same thing in the bladder. The internal sphincter is going to be involuntary, and then, as soon as we're of age, as soon as we're totally potty trained, the external sphincter, for the most part, becomes voluntarily controlled. So like we've been talking about, the bladder serves as a pouch, as a sac for urine. And when it's empty, when we relieve ourselves, go to the bathroom, it collapses and it kind of just shrinks or shrivels up. And we get the same kind of wrinkles and curvatures that we saw inside the stomach, and we call it the same thing. It's called rugae. And what that allows us for is to have a lot of surface area inside the bladder. So when we're on a long car trip and we just use the restroom and we're not going to use the restroom again for another 4, 5, 6 hours, we can hold our urine. So as the urine expands, it presses on the transitional epithelium, allows it to stretch. Also, the rugae allows it to have that increased surface area, which allows it to stretch more without having this huge pressure increase. Now, it's significant pressure increase is what this is saying here. So it does increase pressure. I mean, if you have to go to the bathroom really bad, it is uncomfortable, but it's not significant enough to where you're going to rupture a bladder if you hold it for a while. And then talking about the mucosa or the epithelial lining of the urethra, it does get a little different here. So right at the junction where the urethra meets the bladder, it is still transitional because the bladder is mainly transitional. But for the most part, the urethra is actually pseudostratified columnar epithelium. So kind of rare in the body. But we do have that in the urethra for both male and female. And at the very, very external orifice, basically where urine actually leaves the body, it is stratified squamous epithelium. And remember, stratified squamous is just layers and layers of these flat pancake cells, and their function is protection. So it's just to protect that very outside opening, especially if you're urinating violently, like if you've been holding it for a long time, you do want to protect that very outer lining tissue. And it makes sense that we would have this protective lining, stratified squamous, being located there because of that. So once again, when we talk about the sphincters, we have the internal urethral sphincter. That's going to be involuntary. And the reason why it's involuntary is because it's made up of smooth muscle. And then with the external urethral sphincter, that's going to be voluntary because that is skeletal muscle that is involved with that. Now, the male urethra and female urethra, obviously different sizes, right? The male urethra, because the penile tissue actually exits the pelvic cavity, is a little longer. Also, the male urethra not just carries urine, but it also carries semen for reproductive purposes. So the female urethra is significantly smaller compared to the male. And once again, we'll talk more about, I'll show you a picture with the reproductive chapter when we get here, but there are 3 openings in the perineal or private area of the female. There's the urethra, that's the most anterior, And then if you go a little posterior, you have the vaginal opening. And then if you go more posterior, you'll have the anal opening. So there actually are 3 openings in that area versus guys obviously just have 2. Okay, last slide. Our last topic is micturition. And micturition is just a fancy way of saying peeing. But you do need to know the scientific term. It's also called urination. It's also called voiding. It's all the same. So in order for this to happen, 3 things have to occur at the exact same time. Number 1, you need to have that detrusor muscle in the bladder contract and kind of push down the urine towards that internal urethral sphincter. At the same exact time that's happening, you have to open the internal urethral sphincter. Once again, it's an involuntary muscle, so this is the autonomic nervous system, the parasympathetic nervous system taking place here. And then at the exact same time of all that happening, you need to have voluntary contraction of the external urethral sphincter to actually let it push out of your body. So 2 out of these 3 scenarios or situations involve the autonomic nervous system. So this is more of a parasympathetic response. So if you are fighting or flighting, this is not going to work very well. And that's where people get the stage fright, right? If somebody's looking at you or yelling at you when you're trying to urinate, or you're distracted, or you're moving, you're walking or something like that, it's very hard to pee at the exact same time because your autonomic nervous system is in more sympathetic mode versus the rest, chill, digest, and pee mode. So you have to be in somewhat of a relaxed environment in order for this to happen most of the time. And then the voluntary is just that contraction of those external sphincter muscles. Last note is what actually is controlling this with the help of the autonomic nervous system is the pons, believe it or not. And the pons has 2 nuclei, 2 masses of a whole bunch of cell bodies in them, and one helps us pee and one helps us not pee at all times. And as you can notice, this doesn't really mature until age 2 or even age 3. So for parents trying to potty train infants at age like 1 or age like 15 months, there was articles in Japan that basically showed it's kind of impossible. Not because they're not smart enough at that age or not because they don't understand. It's literally because the neural networks, the connections between their brainstem and their spinal nerves and their bladder aren't fully developed yet. So it takes until about age 2, even up to age 3 and beyond, for these nerves to actually be fully synapsed and connected to where they can say, I have to go to the bathroom and I can hold it or not hold it, that kind of thing. So just takes a little bit of maturation of those nerve fibers and tracts. All right, everyone, that is it for the urinary system. Make sure you study, let your instructor know if you have any questions, and we will see you next time.